The galactic biosphere. Life across the stars. Long before there were planets, before stars and sunlight, the seeds of life were already forming in the darkness. The vast cold spaces between the stars, once thought to be empty, are in fact chemical foundries, where atoms assemble into molecules, and molecules into the precursors of life. Here, at temperatures only a few degrees above absolute zero, the slow choreography of cosmic chemistry unfolds. In these molecular clouds, hydrogen, carbon, oxygen, and nitrogen, the elemental alphabet of biology, begin to write the first lines of the story that will one day lead to DNA, cells, and consciousness. Interstellar molecular clouds are colossal structures, diffuse but enormous, stretching for tens to hundreds of light years, and containing up to 1 million solar masses of gas and dust. Composed mostly of molecular hydrogen, H2, they also harbour trace amounts of carbon monoxide, CO, ammonia, NH3, water vapour, H2O, formaldehyde, H2CO, and hundreds of other molecules. These clouds are the nurseries of both stars and chemistry, where gravity, radiation, and magnetism collaborate to create structure and complexity. In these environments, temperatures often fall to 10 to 20 Kelvin. At such extremes, reactions that would be impossible on Earth proceed through slow quantum tunneling on the surfaces of dust grains, tiny silicate or carbon particles only nanometers across. These grains act as cosmic catalysts, where atoms stick, migrate, and react, forming molecular hydrogen, water ice, methanol, and more complex organic compounds. Layer by layer, these icy mantles accumulate, becoming the chemical scaffolds of future comets and planets. When starlight or cosmic rays strike them, energy triggers further reactions, creating aldehydes, alcohols, and even simple sugars. The void between the stars is thus not empty, but alive with molecular invention. Our knowledge of interstellar chemistry comes not from samples, but from light, specifically the spectral lines emitted or absorbed by molecules. Each molecule vibrates and rotates in characteristic ways, producing signals at precise radio or infrared frequencies. Radio telescopes such as ALMA, Atacama Large Millimeter/Submillimeter Array, and IRAM act as molecular detectors, mapping these emissions across space. In 1968, astronomers first detected ammonia and water vapor in interstellar clouds, marking the dawn of astrochemistry. Soon after came detections of formaldehyde, hydrogen cyanide, and methanol, all molecules essential to prebiotic chemistry. As instrumentation improved, the catalogue grew exponentially. Today, over 300 distinct molecules have been identified in interstellar space, from simple diatomics like CO and CN to complex organics such as formamide, NH2CHO, acetaldehyde, CH3CHO, and even ethyl formate, C2H50CHO, the molecule that gives raspberries their scent. Most astonishingly, detections have revealed aromatic hydrocarbons, ringed carbon structures akin to those found in petroleum and biomolecules, and fullerenes, spherical carbon cages resembling microscopic geodesic domes. These discoveries confirm that the chemical creativity of the cosmos extends far beyond what early chemists imagined. Dust grains are the unsung heroes of interstellar chemistry. Without them, most reactions would stall in the cold vacuum. Their surfaces provide not only contact points but also energy sinks, allowing exothermic reactions to proceed safely without destroying the products. A typical sequence begins when atomic hydrogen adheres to a grain surface. When two such atoms meet, they combine to form molecular hydrogen, H2, the most abundant molecule in the universe. This simple process releases energy, warming the grain slightly, and enabling further reactions. Carbon, oxygen, and nitrogen atoms then accrete and react with hydrogen, forming water, H2O, methane, CH4, ammonia, NH3, and methanol, CH3OH. Over millions of years, these ices accumulate into multilayered mantles, incorporating traces of CO, CO2, and more exotic radicals. When nearby stars ignite, their ultraviolet radiation photolyzes these ices, breaking bonds and creating new radicals that recombine into complex organic molecules, COMs. Laboratory experiments simulating this process, irradiating icy mixtures at cryogenic temperatures, have produced amino acid precursors, simple sugars, and nucleobase analogues. The same chemistry likely occurs in molecular clouds, meaning that life's building blocks begin forming long before planets exist. As gravity pulls regions of a molecular cloud together, they collapse into protostars surrounded by dense envelopes of gas and dust. In these hot cores, temperatures rise to hundreds of Kelvin, causing ices to evaporate and releasing their complex organics into the gas phase. This warm-up phase triggers a chemical explosion. Reactions accelerate, forming new molecules that cannot exist in colder regions. Observations of hot cores, such as those around Orion KL, Sagittarius B2, and IRAS 16293-2422, have revealed astonishing molecular diversity. Sagittarius B2, a massive cloud near the galactic center, contains amino acetonitriol, a precursor to the amino acid glycine, formamide, glycolaldehyde, the simplest sugar, and numerous other prebiotic compounds. The presence of such molecules in star-forming regions suggests that planetary systems inherit a chemical legacy, a starter kit of organic material pre-assembled by interstellar chemistry. Indeed, isotopic analysis of meteorites and comets shows that much of their organic content originated in the interstellar medium, preserved through the violent birth of the solar system. The nebula collapse did not erase the chemistry of the cosmos. It concentrated it. The interstellar medium, far from being chemically inert, is a vast, interconnected network, a galactic ecosystem of molecules. Ultraviolet radiation from stars, shocks from supernovae, and cosmic rays continuously destroy and recreate molecules, driving a dynamic cycle of transformation. Atoms forged in stars are dispersed by explosions, recombine in cold clouds, and form new molecules that eventually condense into planets. This continuity links every stage of cosmic evolution. Stellar death begets molecular birth, and molecular birth seeds planetary life. Astrochemists often refer to this as the molecular universe, where chemistry is the connective tissue between physics and biology. It demonstrates that complexity is not rare. It is an emergent property of matter, wherever energy flows gently enough to preserve bonds. Even in the near absolute zero of space, the universe is restlessly creative. Among the most significant interstellar molecules are those containing both carbon and nitrogen, as they form the backbone of amino acids and nucleobases. The discovery of formamide, NH2CHO, in multiple molecular clouds is particularly exciting, as it is a versatile prebiotic agent capable of producing sugars, nucleobases, and peptides in laboratory conditions. Similarly, cyanoacetylene, HC3N, and hydrogen cyanide, HCN, are fundamental precursors to adenine, one of the building blocks of DNA. Spectroscopic observations reveal that these molecules are not rare, but widespread throughout the galaxy, present in cold, dark clouds, hot cores, and protoplanetary disks alike. This universality suggests that the chemistry of life is not unique to Earth, but intrinsic to the fabric of the cosmos. If organic molecules form wherever carbon, hydrogen, nitrogen, and oxygen coexist, then every newborn star system begins with the same chemical head start that our solar system enjoyed. Interstellar chemistry unfolds over millions of years. In the earliest stages of cloud formation, simple molecules dominate. H2, CO, and small ions. As the cloud ages, dust grains grow and shield interior regions from ultraviolet light, enabling complex organics to form. When gravitational collapse begins, these compounds are released into the gas phase, where they feed the chemistry of new stars and planets. This cyclical process means that every generation of stars enriches the next, not only with heavy elements from supernovae but with preformed molecules. The galaxy itself becomes an evolving chemical organism, each cycle more complex than the last. By the time Earth formed 4.5 billion years ago, the ingredients for life were already billions of years old, inherited from countless previous stars. Life on Earth is not an isolated miracle, but the culmination of a universal chemical narrative. The amino acids in our cells, the sugars in our DNA, the water in our oceans, all trace their lineage to molecular clouds that existed long before the Sun. The same reactions that occur in interstellar ices and hot cores have been reproduced in laboratories, showing that organic complexity is a natural outcome of cosmic physics. In this sense, biology is not separate from astronomy, but its extension. The boundary between star and cell is merely one of scale. The chemical bridge that spans it is the same bridge that connects matter to meaning, from the inert to the living. When we look into a molecular cloud, we are peering not into emptiness, but into the womb of chemistry. The same dust that obscures starlight is also the canvas upon which the first molecules of life are painted. Each spectral line captured by a radio telescope is a signature of connection, proof that life's ingredients are not the privilege of one planet, but the property of the universe itself. Interstellar chemistry is, therefore, both a scientific and a philosophical revelation. It tells us that life is not a sudden emergence, but a gradual awakening, written into the molecular grammar of the cosmos. The stars did not merely give us light. They gave us the raw language from which life could speak. In the silence of the Antarctic ice and the deserts of Australia lie fragments of worlds far older than our own. These meteorites, dark, heavy, and unassuming, are relics from the dawn of the solar system, each one a time capsule sealed 4.5 billion years ago. Within them, scientists have discovered something astonishing. Amino acids, nucleobases, and other organic compounds, formed not on Earth, but in space. These molecules, the raw ingredients of life, traveled across millions of kilometers before falling into our hands. They are messages from the early cosmos, written not in ink, but in chemistry. The revelation that meteorites contain organic material dates back to the early 19th century, but it was in the 1960s that the full significance became clear. In 1969, a brilliant fireball streaked across the sky over Victoria, Australia, scattering fragments of what would become the most famous meteorite of all, the Murchison meteorite. When researchers analyzed it, they found an unexpected richness. Over 70 different amino acids, many not found in terrestrial biology, along with hydrocarbons, alcohols, amines, and carboxylic acids. This discovery changed everything. It proved that the building blocks of life could form independently of Earth, in the cold chemistry of space or within parent asteroids. Murchison was not unique. It was a representative of a vast class of carbonaceous chondrites, meteorites rich in carbon, and volatile compounds that preserve the chemistry of the early solar system. The amino acids found in Murchison, including glycine, alanine, isovaline, and glutamic acid, were racemic, meaning they contained equal proportions of left and right-handed molecules. Life on Earth uses only left-handed L-amino acids, but abiotic synthesis produces both forms equally. This symmetry is crucial. It indicates a non-biological origin, consistent with formation in the interstellar medium or within asteroids, where no life existed. These molecules are older than life itself, precursors awaiting biology, not products of it. Carbonaceous chondrites are fragments of primitive asteroids that never melted or differentiated, preserving their early chemical makeup. Among the most studied are the CM, Mige type, and CI, Ivuna type meteorites, which contain up to 5% carbon by weight, mostly in the form of complex organics. Their mineral structure, rich in hydrated silicates, sulfides, and carbonates, reveals that their parent bodies experienced aqueous alteration, allowing liquid water to circulate through them for millions of years. It was in these transient warm environments that organic synthesis flourished. Laboratory analysis using gas chromatography mass spectrometry, GC-MS, and isotopic ratio mass spectrometry has shown that the carbon in these amino acids is enriched in the heavier isotope 13C and nitrogen in 15N, signatures of non-terrestrial origin. These isotopic fingerprints match interstellar chemistry, confirming that many of the organics formed in space before being incorporated into asteroids. Beyond amino acids, meteorites contain a suite of nucleobase analogues, purines and pyrimidines, essential components of DNA and RNA. In 2011, researchers detected adenine, guanine, and uracil in multiple carbonaceous chondrites. These molecules, once thought too fragile for interplanetary survival, had persisted for billions of years locked within mineral matrices. Their presence demonstrates that nucleic acid precursors were available throughout the early solar system, potentially ready to seed any planet with the right conditions. The synthesis of organic molecules in meteorites likely occurred through a combination of interstellar inheritance and asteroidal chemistry. Many of the simpler molecules, HCN, formaldehyde, methanol, were formed in interstellar clouds and preserved in icy grains that later coalesced into planetesimals. When these bodies warmed slightly from radioactive decay or impacts, the ices melted, creating miniature chemical laboratories. Within these aqueous environments, reactions such as the Strecker synthesis could take place. In this pathway, aldehydes, ammonia, and hydrogen cyanide react to form amino acids. Laboratory simulations of this process under conditions mimicking asteroid interiors have successfully produced the same amino acids found in meteorites, including isovaline and glycine. Other reactions, such as Formose-type polymerization, can yield sugars from formaldehyde, while nucleobase formation can occur via polymerization of HCN. These processes require no enzymes or biological catalysts, only time, heat, and liquid water. The result is a self-organizing chemistry that parallels the first steps toward life, occurring billions of years before biology began. The inventory of extraterrestrial organics. The organic inventory of meteorites is staggering. Beyond amino acids and nucleobases, researchers have identified polycyclic aromatic hydrocarbons, PAHs, ring-shaped carbon compounds common in interstellar dust, making up a significant fraction of cosmic carbon. Carboxylic acids, precursors to fatty acids that form cellular membranes. Aliphatic hydrocarbons, long-chain molecules that resemble components of lipids. Amines, amides, and alcohols. Versatile intermediates in biochemical reactions. Macromolecular kerogen-like material, complex insoluble organic matter that may represent the polymeric residues of prebiotic chemistry. These findings imply that the early solar system was chemically fertile. Every comet and asteroid was a potential factory of organics, churning out molecules that could later rain down on young planets. During the heavy bombardment phase, when Earth was repeatedly struck by such bodies, enormous quantities of carbon-based material were delivered, possibly billions of tons over hundreds of millions of years. The oceans may have literally been salted with cosmic chemistry. One of the enduring mysteries of biochemistry is chirality. Why life on Earth uses exclusively left-handed amino acids and right-handed sugars. Meteorites may hold a clue. Some amino acids found in Murchison and other meteorites show slight enantiomeric excesses of the left-handed form. Though small, a few percent, these asymmetries could represent the initial bias that life later amplified through autocatalysis. Several hypotheses exist for the origin of this asymmetry. One suggests that circularly polarized ultraviolet light in star-forming regions preferentially destroyed one enantiomer over the other. Another points to beta decay radiation from supernovae, which can produce chiral molecules through asymmetric interactions. If such processes imparted a universal handedness, then the chirality of life may ultimately trace back to the physics of starlight. This implies a profound continuity, the handedness of amino acids, and thus the architecture of life itself, could be a cosmic inheritance, not a local accident. Skeptics long argued that amino acids in meteorites might simply be contamination from Earth after landing. To test this, scientists looked for enantiomeric ratios, isotopic signatures, and unusual amino acids, unknown in terrestrial biology. In every case, the extraterrestrial origin held firm. Amino acids like alpha-amino isobutyric acid, AIB, and isovaline, rare or absent on Earth, appear abundantly in meteorites. Their heavy isotopic ratios and racemic mixtures confirm synthesis beyond our biosphere. Additionally, freshly fallen meteorites recovered rapidly, such as Tagish Lake, 2000, and Sutter's Mill, 2012, show the same organic signatures, ruling out long-term contamination. These samples, preserved under sterile conditions, have become chemical libraries for studying the organic evolution of the solar system. The role of meteorites in the origin of life is twofold. They provided both raw materials and chemical templates. When meteorites struck the early Earth, they would have vaporized partially, but much of their organic content, embedded in minerals or enclosed within pores, could survive entry. Experiments simulating atmospheric re-entry and impact conditions confirm that many amino acids remain intact even after intense heating. During the late heavy bombardment, approximately 3.9 billion years ago, Earth was showered with countless tons of carbonaceous material. This cosmic rain, combined with cometary infall, may have delivered a global ocean of prebiotic organics, sufficient to seed the chemical reactions that led to life. The same process likely occurred on Mars and the icy moons, suggesting a shared molecular ancestry throughout the solar system. Meteorites thus represent the delivery system of cosmic chemistry, turning sterile rock into fertile ground. Each fragment that fell to Earth carried within it not only carbon, but also a record of the galaxy's molecular memory. While Murchison remains iconic, modern missions are now bringing back untouched samples from asteroids themselves. In 2020, Japan's Hayabusa, 2 returned grains from the carbon-rich asteroid Ryugu, and NASA's OSIRIS-REX followed in 2023 with samples from Bennu. Preliminary analyses reveal amino acids, carbonates, and complex organics, remarkably similar to those in meteorites, but free from terrestrial alteration. These samples confirm that organic synthesis in space is a universal process, not a rare anomaly. Even more exciting are the isotopic measurements linking these compounds directly to interstellar chemistry. Ratios of deuterium, heavy hydrogen to hydrogen match those found in comets and molecular clouds, demonstrating that the organics on asteroids are cosmically inherited, survivors from the same molecular clouds that birthed the Sun. When viewed across cosmic time, the picture becomes elegant and complete. Simple molecules form in interstellar clouds. They freeze onto dust grains. These grains clump into asteroids. In those asteroids, Liquid water and mild heat transform them into amino acids and sugars. Those bodies, in turn, rain down on young planets, scattering organic seeds into oceans and atmospheres. From there, chemistry continues its ascent toward biology. The meteorites in our museums are therefore not inert relics. They are fragments of the great chemical continuum linking nebulae, planets, and life. They prove that biology did not start from nothing. It began with a gift from the stars. Each amino acid in a meteorite tells a story of persistence across deep time, from the collapse of a molecular cloud through the birth of a solar system to the fall of a stone on a blue world billions of years later. In those molecules lies an unbroken thread connecting stellar nucleosynthesis to cellular metabolism. When scientists hold a meteorite under the microscope, they are not just studying a rock. They are reading a chemical autobiography of the universe. Within that carbon, the cosmos speaks in the language of life. You are not an accident. You are chemistry come alive. For most of human history, comets were omens, ghostly visitors from the outer dark, portents of disaster and change. But in the modern age, they have been reimagined not as harbingers of death, but as carriers of life. These icy wanderers, forged in the frozen outskirts of the solar system, preserve some of the oldest and most pristine material from its birth. They are time capsules of the early solar nebula, holding within their frozen nuclei a chemical record of the same processes that built the planets, and perhaps the molecules that built us. Comets are more than frozen rocks. They are repositories of organic chemistry, and they may have played a decisive role in turning Earth's sterile surface into a living world. The theory that comets and asteroids seeded our planet with water and organics, the cosmic seeding hypothesis, bridges astronomy, chemistry, and biology in one grand narrative: life as a natural continuation of cosmic evolution. Comets are composed primarily of water ice, mixed with dust, carbon compounds, and frozen gases, such as carbon monoxide, carbon dioxide, methane, and ammonia. The classic dirty snowball model, proposed by Fred Whipple in 1950, remains accurate but understated. Comets are miniature laboratories of organic synthesis, where simple molecules have been irradiated and reprocessed for billions of years. Their origins trace back to the outer solar system reservoirs, the Kuiper Belt and the Oort cloud, where temperatures are so low that even volatile compounds freeze solid. These regions act as cosmic freezers, preserving the primitive chemistry of the solar nebula in its most unaltered form. When gravitational disturbances send a comet inward toward the Sun, heat vaporizes these ices, creating the brilliant tales that have captivated observers for millennia. But it is within those dark, compact nuclei, typically only a few kilometers across, that the chemical secrets of the early solar system are kept. When spacecraft first analyzed cometary material, the results were astonishing. The Giotto mission, 1986, to Comet Halley, revealed that its nucleus contained complex hydrocarbons, chains of carbon and hydrogen that resemble kerogen and tar. The dust released by Halley contained CHON particles, shorthand for carbon, hydrogen, oxygen, and nitrogen, the very elements of biology. Subsequent missions confirmed and expanded this discovery. In 2014, the Rosetta spacecraft and its lander, Philae, became the first to orbit and touch down on a comet, 67P/Churyumov-Gerasimenko. Its instruments detected a rich array of organic molecules, including glycine, the simplest amino acid, methylamine, formamide, and a suite of carbonyl and nitrogen-bearing compounds. Glycine's detection was particularly important. It demonstrated that amino acids can form and survive in the vacuum of space, shielded within ice and dust. Comet 67P's water vapor was also found to contain a deuterium to hydrogen DH ratio, 3 times higher than Earth's oceans. This indicated that not all comets contributed significantly to Earth's water, but some, especially those from the Kuiper belt, like Comet Hartley, too, have D/H ratios that match ours closely. Thus, comets likely contributed both water and organic molecules, but their relative contributions may vary by family and region of origin. Cometary ices are not inert. They are chemical reactors, continuously modified by cosmic rays and ultraviolet light. Over billions of years, this radiation drives the synthesis of complex organics through energetic processing. Laboratory experiments simulating these conditions, bombarding icy mixtures of H2O, CH3OH, NH3, and CO2 with UV light or high-energy particles, produce a rich array of amino acids, sugars, and nucleobase precursors. When these ices are warmed during a comet's perihelion passage, the molecules trapped within are released into space as gas and dust, forming organic-rich comets. Some of this material rains back onto the comet's surface, where it polymerizes further into tar-like residues, a process that may have occurred on countless comets over billions of years, gradually enriching their interiors with prebiotic chemistry. Such chemistry likely began before the solar system existed, in the parent molecular cloud from which the Sun was born. In that sense, comets are archaeological fragments of the interstellar medium, carrying ancient organic molecules across eons of galactic time. Roughly 4 billion years ago, during the epoch known as the Late Heavy Bombardment, the inner solar system was a shooting gallery. Vast numbers of comets and asteroids, destabilized by the migration of the gas giants, rained down upon the terrestrial planets. For hundreds of millions of years, the Moon, Mars, Mercury, and Earth were pummeled by icy projectiles, a storm of cosmic debris that reshaped their surfaces and atmospheres. For Earth, this bombardment may have been paradoxically creative. While many impacts vaporized oceans and crust, they also delivered vast quantities of volatiles and organics, potentially hundreds of trillions of tons of carbon, nitrogen, and water. Models suggest that up to 10% of Earth's early atmosphere and hydrosphere may have been supplied by cometary material. More importantly, laboratory simulations and computer models show that organic molecules can survive impact delivery. Even at speeds of tens of kilometers per second, portions of a comet's nucleus can remain intact, especially when entering at shallow angles or fragmenting in the atmosphere. The result, amino acids and other organics embedded in impact debris, could have rained gently into the oceans, enriching them with prebiotic material. Thus, comets may have acted as cosmic couriers, transferring chemistry from the outer solar system to the inner worlds, a process that likely repeated across countless planetary systems. In recent years, astronomers have detected interstellar visitors, comets not bound to our Sun, but passing through from other star systems. The first, Oumuamua, discovered in 2017, and the second, Comet Borisov, in 2019, demonstrated that the exchange of material between stellar systems is real. Borisov's composition, rich in carbon monoxide and water, was nearly identical to that of solar system comets. This finding has profound implications. If interstellar comets are common, then organic molecules and even microbial life in principle could circulate throughout the galaxy. The Milky Way might be chemically interconnected, its planets and comets exchanging molecular material like pollination across cosmic distances. Life, if it arises somewhere, may not stay confined there forever. Comets are not merely delivery systems. They also shape planetary environments in subtler ways. Their impacts can create transient atmospheres, trigger hydrothermal systems, and deposit minerals that catalyze prebiotic reactions. The carbonaceous dust they shed can darken icy surfaces, altering albedo and promoting melting. On early Earth, such effects could have accelerated the transition from sterile geology to chemical complexity. Even today, comets continue to influence planets. Observations of Jupiter's atmosphere after the impact of Comet Shoemaker-Levy 9, 1994, revealed new chemical species, demonstrating that cometary collisions can alter planetary chemistry on short timescales. If similar impacts occurred frequently in the early solar system, they would have created chemical diversity and disequilibrium, essential conditions for life's emergence. NASA's Stardust mission, 1999 to 2006, provided the first direct samples of cometary material, capturing dust from Comet Wild 2 and returning it to Earth. Laboratory analysis revealed not only silicate minerals but also glycine, aliphatic hydrocarbons, and nitrogen-bearing organics. These findings confirm that the same organic molecules found in meteorites are also present in comets, further linking interstellar and solar system chemistry. The Rosetta mission extended this connection. Among its most striking discoveries were phosphorus, a key element of DNA and cell membranes, and volatile organic compounds such as formaldehyde, formic acid, and acetone. Together, these findings paint a picture of comets as chemical reservoirs, containing nearly all the molecular precursors needed for life: water, carbon, nitrogen, oxygen, sulfur, and phosphorus, the complete CHN-OPS suite. Comet 67P's surface, though harsh and airless, showed evidence of organic crusts formed by ultraviolet radiation and thermal cycling, essentially carbon-rich coatings not unlike primitive tar. These crusts, exposed to sunlight and transient liquid phases in microenvironments, could have hosted catalytic chemistry. In this way, even within a comet itself, proto-biochemical processes may briefly occur. The cosmic continuum, from icy grains to living worlds. When we trace the history of cometary organics, we see an elegant continuum. In the cold interstellar medium, molecules form on dust grains. Those grains accrete into icy planetesimals, the embryos of comets. In the outer solar system, radiation and time enrich those ices with complex organics. Through impacts and delivery, these molecules are transferred to young planets. On those planets, energy, water, and stability allow chemistry to cross the final threshold into biology. Each step is a natural consequence of physical laws. No miracles required, only time and temperature. Comets are therefore agents of continuity, linking cosmic physics to planetary chemistry and ultimately to biology. They embody the idea that life is a universal chemical process, not a singular event. The thought that life's ingredients were delivered by comets transforms our view of the cosmos. It suggests that the universe is not merely a backdrop for life, but a participant in its creation. Every comet that streaks across our skies may be a symbol of this continuity, a fragment of the deep molecular past that once gave birth to us. In this light, comets are midwives of life, carrying the nutrients of creation from one world to another. They blur the boundary between astronomy and biology, reminding us that the story of life did not begin on Earth's surface, but in the chemistry of the cosmos. When the first rain fell on the young Earth, it may have mingled with molecules that had traveled across interstellar space for billions of years. In those droplets, the universe was remembering itself. Today, missions like Comet Interceptor, ESA 2029, and proposed sample return projects aim to analyze pristine cometary material directly, unaltered by atmospheric entry. Each new study refines our understanding of how life's building blocks survive and propagate through space. The ultimate goal is to map the organic inventory of the solar system, and to determine how widespread life's chemistry truly is. What we are finding is humbling. Life's ingredients are everywhere, not confined to planets, but drifting between stars, cycling through ice, dust, and radiation. The boundary between living and non-living chemistry becomes ever thinner. When viewed from this cosmic perspective, Earth is not an isolated oasis, but one node in a galactic experiment, where comets and asteroids act as couriers of chemical potential. The story of cometary seeding reveals a universe that recycles itself into higher forms of complexity. The dust of dead stars becomes the ice of comets. That ice becomes the rain of molecules upon new worlds. And those molecules, given time and energy, awaken as life. It is a cycle both scientific and poetic, an unbroken chain from supernova to cell. When we gaze upon a comet's luminous tail stretching across the night sky, we are not witnessing an alien intruder, but a returning ancestor, a fragment of our own beginnings. Its dust may once have drifted in the same molecular cloud that gave rise to Earth, and its ices may hold the memory of life's first chemistry. Every comet that graces our skies whispers the same message. Life did not emerge in isolation. It was sown among the stars. The birth of our solar system was not a single event, but a prolonged experiment, a vast cosmic laboratory in which matter, energy, and time collaborated to create the conditions for life. Long before the first cell divided, before Earth cooled or oceans formed, the elements themselves were mixing, condensing, and reacting in a dance of chemistry on a scale beyond imagination. In the nebular mists surrounding the infant sun, dust, gas, and ice were the reagents. Gravity, heat, and radiation were the catalysts. And the outcome was nothing less than the architecture of a living system. To understand how life arose, one must first understand that the early solar system was already a molecular crucible, processing and redistributing organics inherited from interstellar space. In this grand experiment, the distinction between physics and biology dissolves. The same forces that built planets also built the chemistry of potential life. About 4.6 billion years ago, a fragment of a molecular cloud collapsed under its own gravity, triggering the formation of the Sun. The leftover material flattened into a rotating disk, the solar nebula, spanning tens of billions of kilometers. Within this swirling disk, temperatures ranged from thousands of degrees near the center to less than 100 Kelvin at its outer edges. Across this gradient, chemistry unfolded in zones, each with its own character and products. Near the proto-sun, intense radiation drove off volatiles and melted silicates and metals, forming the seeds of the terrestrial planets. Farther out, where it was cooler, ices could condense. Water, ammonia, methane, and carbon dioxide, forming the cores of gas giants and the icy bodies that would populate the Kuiper belt. Between these extremes, in the region that would become the asteroid belt, conditions were ideal for complex organic reactions. Warm enough for liquid water to exist transiently within planetesimals, yet cool enough to preserve delicate molecules. This was the chemical frontier of the early solar system. Modern astronomy, through infrared and millimeter wave telescopes such as ALMA and JWST, allows us to observe young stellar systems in other parts of the galaxy, snapshots of our own origins frozen in time. These protoplanetary disks reveal intricate rings and gaps where planets are forming, and their spectra show the same organic molecules found in interstellar clouds: formaldehyde, acetylene, methanol, water vapor, hydrogen cyanide, and formamide. This confirms that the chemistry of life is not confined to a single place. It is cosmically reproducible. The same compounds that once condensed in our solar nebula are forming now around countless young stars. Each disk is a natural reactor, where ultraviolet light from the central star triggers photochemistry, cosmic rays drive ion molecule reactions, and dust grains act as catalytic surfaces. Across millions of years, this interplay creates the inventory of organics that will seed future planets, moons, and comets. Within the cooling nebula, microscopic dust grains aggregated into kilometer-sized planetesimals, the building blocks of planets. Some of these, particularly the carbon-rich ones in the outer asteroid belt, became micro-laboratories of prebiotic chemistry. Radioactive isotopes, like aluminum-26, provided internal heat, melting ice, and generating short-lived oceans within these bodies. In that liquid environment, organic synthesis accelerated. As discussed earlier, processes like Strecker synthesis and Formose reactions converted simple compounds such as formaldehyde, hydrogen cyanide, and ammonia into amino acids, sugars, and other complex molecules. Minerals within these bodies, clays, sulfides, and carbonates, acted as catalysts and templates, guiding reactions toward greater complexity. The products of these asteroid oceans were preserved when the bodies cooled and solidified, trapping their organics in stone. Billions of years later, fragments of these primitive worlds would fall to Earth as carbonaceous meteorites, bearing the record of this ancient chemistry. Thus, the first laboratories of prebiotic synthesis were not on planets, but in the tiny, dark interiors of asteroids, each one an isolated test tube orbiting the young sun. One of the defining features of this cosmic laboratory was its temperature gradient, which determined where different molecules could exist and interact. Close to the sun, in the rockline region, within 1 astronomical unit, temperatures exceeded 1,500 kelvins, allowing only refractory materials like iron, nickel, and silicates to condense. This region birthed the terrestrial planets, metallic and rocky, but largely devoid of volatiles. Farther out, near 3 astronomical units, lay the snow line, where water vapor could freeze. Beyond this threshold, ices became abundant, enabling the formation of hydrated minerals and organic-bearing planetesimals. Still farther, beyond 10 astronomical units, temperatures dropped low enough for methane, ammonia, and carbon monoxide to condense. This region, the realm of the gas giants and icy moons, became a repository of organic-rich ices. Each of these zones functioned like a distinct chemical bench within the same cosmic laboratory, contributing unique compounds to the grand experiment. As the solar system evolved, migration of planets and mixing of debris blurred these boundaries, spreading organic material inward toward the nascent Earth. This chemical transport ensured that no planet formed in isolation. Each inherited the molecular legacy of the entire disk. The early solar system was anything but serene. Collisions were constant, violent, spectacular, and essential. Each impact reprocessed material, melting rock, vaporizing ice, and redistributing elements. Paradoxically, destruction was the engine of creation. Every collision was a chemical reset, exposing fresh mineral surfaces, liberating trapped gases, and creating new conditions for reaction. These cataclysms also enabled mixing across zones. Material from the cold outer regions, rich in ices and organics, was scattered inward by the gravitational influence of Jupiter and Saturn, colliding with the dry, rocky inner bodies. This process may have delivered the first water and carbon compounds to the young Earth and Venus, providing the precursors for prebiotic chemistry. The bombardment of organic-rich comets and asteroids turned the early inner solar system into a planetary-scale reaction vessel. Simultaneously, massive impacts, like the one that created the Moon, produced extreme heat and vaporization, but also chemical gradients that could later drive synthesis as the planet cooled. In short, the chaos of early planetary formation was also the engine of biochemical potential. Meteorites, comets, and interplanetary dust particles carry isotopic fingerprints that allow scientists to reconstruct this early chemical evolution. Ratios of deuterium to hydrogen, D/H, 13C/12C, and 15N/14N vary systematically across different bodies, revealing where and how their organic compounds formed. For example, high DH ratios in comets and certain meteorites indicate origin in cold, interstellar-like environments, whereas lower ratios in planetary materials suggest warmer, inner-solar conditions. The fact that Earth's oceans have an intermediate DH ratio implies that multiple sources contributed, perhaps both comets and asteroids, blending organics from across the solar nebula into one planetary mixture. These isotopic signatures also trace the inheritance of interstellar material. Many organics retain anomalies, matching those observed in molecular clouds, confirming that the solar system's chemistry was not reset during formation, but preserved and elaborated upon. Life's ingredients thus have an ancestral lineage reaching back to pre-solar space. While radiation and temperature provided energy, minerals provided structure. In the early solar system, fine-grained clays, sulfides, and iron-nickel compounds acted as catalysts, facilitating the assembly of organic molecules. Minerals like montmorillonite could polymerize nucleotides into short RNA-like chains. Pyrite and greigite could drive redox reactions central to metabolism, and metal sulfides could catalyze the formation of amino acids and simple hydrocarbons from carbon monoxide and hydrogen. In this sense, the boundary between geochemistry and biochemistry was blurred even before life began. The solar system itself was a giant geochemical incubator, where inorganic matter repeatedly organized into patterns resembling the precursors of living systems. These same mineral-catalyzed reactions may later have been replicated in Earth's hydrothermal vents, continuing a process that began long before the planet solidified. Over millions of years, the solar nebula cooled, dissipated, and gave way to a structured planetary system. But its chemical legacy persisted, not as isolated molecules, but as a distributed system of organic reservoirs. Comets in the Oort cloud, asteroids in the main belt, carbon compounds on the outer moons, and organic hazes on worlds like Titan. Each preserved a piece of the puzzle. This distributed network of organic-rich environments can be seen as the solar system's extended laboratory, a self-sustaining experiment that continues to this day. Every new mission, from Rosetta to OSIRIS-REx to Dragonfly, explores a different bench of that ancient laboratory, revealing the persistence of chemical diversity across billions of years. What emerges from this story is not randomness, but self-organization. The solar system evolved from a turbulent disk into a stable architecture, and its chemistry evolved from simplicity into complexity. The two processes were linked. As gravity brought order to matter, chemistry brought order to molecules. The emergence of planetary orbits and the emergence of prebiotic molecules were parallel aspects of the same tendency toward structure. Viewed this way, the solar system was not merely a setting for life to appear later. It was already behaving like a living system, cycling energy, exchanging matter, and building complexity from chaos. Each feedback loop, each gradient of heat and radiation, was a chemical heartbeat that echoed across millions of kilometers. By the time the first oceans formed on Earth, the experiment had already been running for hundreds of millions of years, and the reagents were ready. To call the early solar system a laboratory is not metaphor, but description. Every planet, moon, and asteroid was a beaker in the grand experiment of creation. The reactions that occurred within them were guided not by intention, but by the inherent logic of chemistry, a logic that seems to favor complexity, organization, and replication. In that sense, the solar system was not designed for life, but conducive to it, structured by physical laws that made life almost inevitable. The line between geochemical evolution and biological evolution is not sharp, but continuous. Life, as it emerged on Earth, was simply the latest expression of a chemistry that had been unfolding since the first dust grains met in the nebular dark. Today, scientists can trace that continuity directly. The same isotopes and molecular ratios found in ancient meteorites appear in the amino acids and nucleobases of living organisms. The carbon in our bodies once drifted in interstellar clouds. The iron in our blood was forged in supernovae. The calcium in our bones condensed from the nebular disk. Every atom of life has passed through the crucible of the solar system's chemical past. To study the early solar system is therefore to study the prehistory of biology. It reveals that the origin of life was not an isolated miracle, but the natural culmination of a cosmic experiment billions of years in the making. The chemistry that began in the darkness between stars was refined in the solar nebula and perfected on planetary surfaces. A seamless progression from matter to molecule, from molecule to metabolism. When we hold a meteorite, examine a comet's dust, or model the composition of a protoplanetary disk, we are peering into that ancient laboratory, the one that ran without walls, without witnesses, and without pores. Its final product was not a mineral or a molecule, but awareness, matter that could one day look back and understand its own formation. The solar system, it turns out, was not merely born. It experimented itself into existence. Few ideas in the history of science have stirred the imagination, quite like panspermia. The proposition that life did not originate on Earth but was seeded from elsewhere. The concept, both ancient and modern, stretches the story of life from the boundaries of biology to the scale of the cosmos itself. It asks a profound question. If the universe is rich in organic molecules, could it also be rich in life-bearing spores, traveling between worlds, on stones, dust, or comets? In a sense, panspermia is less about denying life's earthly origins than about expanding its context. It suggests that the same cosmic processes that created amino acids and nucleobases might have gone further, producing actual microbes, perhaps long before Earth was ready for them. But is this vision scientific reality or poetic metaphor? Is panspermia a mechanism or merely a myth retold in modern terms? The answer lies somewhere between the rigor of physics and the romance of philosophy. The roots of panspermia go back to ancient Greece, where philosophers like Anaxagoras proposed that seeds of life, spermatopandan, exist everywhere in the cosmos and can generate living beings when they find suitable environments. In this worldview, life was not a local anomaly, but a universal principle. The idea resurfaced in the 19th century, when Lord Kelvin and Hermann von Helmholtz speculated that microbes could be transported through space by meteoroids, surviving planetary ejections and impacts. Later, Svante Arrhenius, 1903, formalized the concept of radiopanspermia, proposing that bacterial spores could be pushed through space by starlight pressure. These early thinkers were not mystics, but physicists and chemists, grappling with the improbability of spontaneous biogenesis on a single planet and the vastness of interstellar space as a transport medium. In the 20th century, as microbiology and astronomy advanced, the hypothesis gained new life. Fred Hoyle and Chandra Wickramasinghe championed the modern version of panspermia, arguing that comets and interstellar dust are reservoirs and vectors of life-bearing material. Their claims, controversial but stimulating, included the suggestion that viruses, bacteria, and even epidemics could originate from space. carried by cometary debris entering Earth's atmosphere. Though these extreme versions lack empirical support, they reignited serious discussion of life's cosmic dispersal. Among the various formulations of the theory, lithopanspermia, the transfer of microorganisms within rocks ejected by impacts, stands as the most physically plausible. We now know that meteorite exchange between planets is common. Over 150 Martian meteorites have been identified on Earth, ejected by asteroid impacts on Mars and later captured by Earth's gravity. The travel time for such rocks can range from thousands to millions of years, long enough for microbial dormancy but short enough to preserve some potential viability. Laboratory experiments have demonstrated that certain microorganisms, particularly spore-forming bacteria such as Bacillus subtilis and Deinococcus radiodurans, can withstand extreme conditions of temperature, radiation, vacuum, and shock pressure. Encased within porous rock or beneath layers of dust, microbial spores could be shielded from UV radiation and cosmic rays. If ejected from a planet's surface by an impact, and later re-entering another atmosphere gently enough, they could, in principle, survive interplanetary transfer. Computer models further support this possibility. Ejecta from Mars, for instance, could reach Earth within a few 100,000 years, a blink in geological time. The AL-H84001 meteorite, discovered in Antarctica in 1984, famously contained carbonate globules and magnetite crystals that some interpreted as potential microbial fossils. While that claim remains unproven, the meteorite's isotopic composition and aqueous alteration confirm that it once harbored liquid water, a crucial prerequisite for biology. Whether or not it carried actual life, it proved the transport mechanism is real. If lithopanspermia can occur between Earth and Mars, it likely happens across the solar system. Impacts on Europa, Enceladus, Titan, and other icy moons could eject frozen material into interplanetary space, some of which might eventually encounter habitable niches elsewhere. Even Venus, whose atmosphere may once have been temperate, could have exchanged material with Earth during its ancient volcanic outbursts. In this light, the solar system behaves as a biological network, an ecosystem in which matter and possibly microbes circulate between worlds. This interconnectivity has profound implications. If life arose on any one of these worlds, it could have spread naturally to the others. Alternatively, if prebiotic chemistry reached a critical threshold somewhere, but failed to ignite biology, fragments of that chemistry could still have fertilized other environments. Life may not have begun multiple times independently, but migrated and diversified, like seeds carried on a galactic wind. More radical still is interstellar panspermia, the idea that life can travel between stars. The physics here is daunting. Even at velocities achieved by ejected meteoroids, a few kilometers per second, crossing the nearest stellar distances would take millions to tens of millions of years. During such times, cosmic rays would bombard any exposed organism with lethal doses of radiation, breaking down DNA and cell membranes. Without extraordinary shielding colossal kilometers of rock or ice, survival seems unlikely. Yet not impossible. Certain bacterial spores and tardigrades have demonstrated remarkable endurance, surviving vacuum, freezing, and radiation exposure in experiments aboard the International Space Station, ISS, and simulated deep space conditions. Organic molecules, too, show surprising resilience. Amino acids, sugars, and nucleobases embedded in meteorites have persisted for billions of years. While intact cells may be fragile, molecular life, the chemical precursors, could easily cross interstellar distances. Thus, a modified form of panspermia, molecular panspermia, is entirely plausible. This scenario aligns with the concept of chemical continuity. Rather than living organisms traversing space, it is information-bearing chemistry that travels, a molecular seed awaiting suitable conditions to evolve into biology again. This bridges the philosophical gap between abiogenesis and panspermia, showing them not as opposites, but as complementary phases of one universal process. A provocative variant, proposed by Francis Crick and Leslie Orgel in 1973, is directed panspermia, the notion that intelligent civilizations might deliberately seed other worlds with life. This hypothesis arises not from mysticism, but from probability. If life can arise and evolve intelligence elsewhere, such beings might use microorganisms as biological ambassadors. The process would involve dispatching resilient spores or engineered cells aboard spacecraft, or probes capable of surviving interstellar travel. While speculative, directed panspermia raises an interesting inversion. If others could seed us, perhaps we could seed others. In the age of interplanetary exploration, humanity now possesses the technology to carry microbes beyond Earth, whether intentionally or accidentally. Every spacecraft, despite sterilization efforts, risks forward contamination, potentially exporting Earth's biosphere to Mars, Europa, or Titan. In this way, we are already agents of panspermia, consciously or not, extending the reach of life beyond its native cradle. Despite its appeal, panspermia faces formidable challenges. The vacuum of space, intense radiation, and extreme cold are lethal to most known organisms. While spores and extremophiles exhibit remarkable durability, the combination of all factors over millions of years reduces survival probability to near zero. Experiments aboard the ISS, such as EX, POSE-E and Tanpopo, show that some spores can survive up to several years. In space, if shielded, but full interplanetary or interstellar journeys are far longer. Atmospheric entry is another barrier. A rock entering at high velocity experiences surface temperatures exceeding 1,500 degrees Celsius. Only microbes buried several centimeters deep could survive. And even then, only a small fraction. Yet, a small fraction, across billions of impacts, might suffice. Life needs only a few surviving cells to establish itself on a new world. Thus, panspermia is not impossible, merely improbable. But the universe operates on vast numbers and vast timescales. Even improbable events can become inevitable when multiplied across billions of years and trillions of worlds. Modern astrobiology increasingly views panspermia not as a singular mechanism, but as a statistical inevitability. The ingredients of life, water, carbon, and organics, are universal. Planetary collisions and material exchange are frequent. Microbial resilience is extraordinary. The Milky Way may thus function as a biochemical ecosystem, where matter and potential life circulate continuously. If life arose early on one world, panspermia could distribute it throughout local clusters of stars. Each inhabited system would become a new source of dispersal, creating biological domains within the galaxy, regions where life shares common ancestry. Over billions of years, this could lead to a cosmic tree of life, spanning multiple planetary systems. DNA, or an analogue thereof, could be the universal language of biology across worlds. In this framework, Earth's life is not unique, but part of a wider galactic biosphere, connected through ancient exchanges of matter. This is not mysticism. It is cosmic ecology, the natural extension of the same recycling processes that govern planets and stars. Panspermia also raises a philosophical paradox. If life came from elsewhere, where did it begin? The theory merely relocates the problem of origin, rather than resolving it. Yet in doing so, it reframes the question itself. Perhaps life did not begin somewhere but is a perpetual phenomenon, an emergent property of matter that has existed since the early universe. In this view, life is not a rare outcome but an intrinsic feature of the cosmos, like gravity or magnetism. Each new world is not the first to live, but the latest to awaken. This vision blurs the line between science and metaphysics, but remains grounded in observation. The universe is chemically alive. Organic molecules form in interstellar clouds, assemble on icy grains, and are delivered to planets. Whether these molecules cross the threshold into biology depends only on environmental opportunity. In such a universe, panspermia is not an exception, but the natural extension of chemical continuity. Critics rightly note that no direct evidence exists of living organisms arriving from space. All confirmed life remains terrestrial. Abiogenesis, the independent origin of life on Earth, remains the simplest explanation, consistent with known chemistry. Yet the boundary between local and cosmic origins is narrowing. If the organic precursors of life were delivered from space, then life's spark may have been local, but its fuel was cosmic. Panspermia, therefore, need not be literal to be meaningful. It symbolizes the continuity between cosmos and cell, between the birth of stars and the birth of biology. Even if microbes never traveled between planets, the molecules that became us surely did. In that sense, panspermia, stripped of speculation and excess, is not merely romantic. It is a poetic reflection of cosmic realism. The ultimate test for panspermia will come from comparative biology beyond Earth. If we find life on Mars, Europa, or Enceladus, the key question will be, does it share our biochemistry? If Martian microbes use DNA, RNA, and the same 20 amino acids, the implication would be clear: a shared ancestry, a product of interplanetary exchange. If, however, alien life employs a fundamentally different molecular architecture, it would argue for independent origin and a deeper universality of biogenesis. Either outcome affirms the same truth. The cosmos is creative. Whether through seeding or self-assembly, life arises wherever chemistry and environment align. Panspermia, then, is not a fantasy, but a framework, a recognition that life is continuous with the universe that made it. In the end, panspermia may not answer the question of life's origin, but it changes the scale at which we ask it. It invites us to see biology not as an isolated phenomenon on a single planet, but as a cosmic process, shaped by billions of years of molecular migration. It unites the dust of comets, the minerals of meteorites, and the cells of organisms in one continuous narrative, the universe knowing itself through chemistry. Romantic? Perhaps. But every great scientific idea begins with a romantic intuition that the world is larger, older, and more interconnected than we imagine. Panspermia reminds us that life's home may not be Earth alone, but the entire cosmos, and that in the fall of a meteor or the glow of a comet's tail, we are witnessing not the arrival of strangers, but the return of our own beginnings. If the story of life is written in chemistry, then astrochemistry is its prologue, the earliest draft of a narrative that began long before Earth, long before the Sun, even long before the galaxy as we know it. Across the cold void of interstellar space, atoms forged in ancient stars have been combining, breaking and recombining for billions of years, weaving the molecular fabric that would one day breathe, grow, and think. This is the great continuity of matter and life, a single unbroken chain from supernova to cell, from cosmic dust to consciousness. To understand life in its fullest sense, we must look not downward to the molecule or upward to the cell, but outward, to the cosmic chemistry that made all later complexity possible. Every element essential to life was born in the heart of a star. Hydrogen and helium emerged from the Big Bang, but carbon, nitrogen, oxygen, phosphorus, sulfur, and iron, the alphabet of biology, were forged in stellar furnaces through nuclear fusion. When massive stars reached the end of their lives, they exploded as supernovae, scattering these elements into the galaxy. Over eons, this material mixed with gas and dust, cooled, and condensed into new stars and planetary systems. Each generation of stars thus enriched the galaxy's chemical inventory, gradually transforming a universe of simplicity into one capable of supporting life. The atoms in our blood once resided in red giants. The calcium in our bones once drifted through space as dust. The oxygen we breathe was born in the fusion shells of massive suns. The universe, in a literal sense, became alive through its own recycling. We are its latest incarnation. The cosmos reorganized into awareness. This chemical continuity, the seamless transition from stellar matter to biological matter, is the domain of astrochemistry, the discipline that bridges astrophysics, chemistry, and biology into a single evolutionary framework. It reveals that life is not an anomaly, but a consequence of the universe's innate tendency toward complexity under constraint. In the interstellar medium, the chemistry of life's raw ingredients unfolds on the smallest scales and in the harshest conditions. Atoms meet on the surfaces of dust grains, forming water, formaldehyde, and methanol. Ultraviolet photons and cosmic rays inject energy, catalyzing the creation of amino acid precursors and aromatic hydrocarbons. What would take seconds in a warm laboratory takes thousands of years in space. But time is one resource the universe possesses in abundance. Astrochemistry demonstrates that the laws of chemistry operate universally. The same equations govern a nebula and a neuron. The difference lies only in concentration and complexity. The discovery of hundreds of organic molecules in molecular clouds, including formamide, acetaldehyde, and even glycolaldehyde, a sugar, confirms that organic synthesis is a natural outcome of physical law, not a biological accident. The universe is a laboratory operating continuously, producing molecules capable of self-organization, wherever temperature, density, and time align. Stars, planets, and living organisms are simply different levels of this same chemical experiment, one that has been running for nearly 14 billion years. When this interstellar chemistry entered the solar nebula, it did not stop, it diversified. Within the protoplanetary disk, each region acted as a separate reactor, converting inherited molecules into new forms. Warm inner regions yielded silicates and metals. Cold outer regions preserved water and carbon compounds. As planetesimals formed, heating and cooling cycles drove further reactions, turning simple volatiles into amino acids, sugars, and complex hydrocarbons. These molecules, locked in comets and asteroids, later bombarded the young Earth, an act of chemical delivery that completed the cosmic circuit from star to sea. Thus, the chemistry of the cosmos became the chemistry of the planet. The line between astro and bio is arbitrary. Every drop of water, every carbon chain, every molecule of DNA is part of an unbroken continuum, stretching back to the first stars. The periodic table is the shared language of both stars and cells, and astrochemistry is its grammar. The key insight of astrochemistry is that complexity is inevitable. When energy flows through matter under stable yet dynamic conditions, structure emerges spontaneously, from convection cells to snowflakes to amino acids. This principle, known as self-organization, operates across all scales. In space, it governs the formation of molecular clouds and planetary disks. On Earth, it governs the assembly of biomolecules and ecosystems. Life, in this context, is the highest expression of a universal tendency toward order and pattern. When prebiotic molecules arrived on the early Earth, They entered an environment rich in energy gradients, lightning, ultraviolet radiation, hydrothermal vents. These inputs drove molecular selection. Some reactions persisted, others failed. Over time, networks of chemistry that could store and transfer information emerged, the precursors of metabolism and replication. The leap from organic molecule to living cell was immense, but not miraculous. It was a phase transition in a system already primed for complexity by cosmic chemistry. The continuity here is profound. The same thermodynamic principles that built galaxies also built genes. Both are systems that reduce entropy locally by exporting it globally, maintaining order through the flow of energy. In this sense, life is not the opposite of physics. It is physics made intricate. Astrochemistry does not end at the solar system's edge. Observations across the Milky Way reveal that the same molecular species found in our local clouds exist in distant star-forming regions: Orion, Taurus, Perseus, and Sagittarius. The galaxy itself functions as an enormous, distributed chemical network, with material cycling between stars, nebulae, and planets. Each cycle adds new complexity. Over billions of years, such processes could give rise not just to prebiotic chemistry, but to multiple origins of life. If the building blocks are everywhere, then life may be widespread, not as identical replicas of Earth biology, but as diverse chemical expressions of the same universal rules. The discovery of exoplanets with atmospheres rich in water vapor, methane, or ammonia strengthens this picture. These are not isolated accidents, but chemical echoes of the same processes that created our world. Astrochemistry, therefore, provides the foundation for a universal biology, one that recognizes life as an emergent property of galactic chemistry. In this view, the Milky Way is not a sterile collection of stars, but a living system, slowly awakening across time and space. One of the most striking consequences of this cosmic perspective is the realization that consciousness itself is part of the same continuum. The neurons that think are made of carbon and nitrogen, the same elements that formed in ancient stars and once drifted as molecules in interstellar clouds. The oxygen carried by hemoglobin was once locked in the ice of a comet. The phosphorus in DNA was once trapped in the dust of the solar nebula. Every thought, every breath, every heartbeat is the universe processing its own memory. This realization transforms astrochemistry from a purely scientific field into a philosophical bridge. It links the material and the meaningful, demonstrating that the emergence of life and mind is not an interruption of nature, but its natural continuation. The cosmos has in effect become self-aware through chemistry. From the standpoint of chemistry, the universe exhibits a single overarching principle: continuity through transformation. Hydrogen becomes helium in stars. Carbon becomes complex molecules in space. Molecules become cells on planets, and cells evolve into organisms capable of reflection. At each stage, no new element of magic is introduced, only new configurations of matter and energy. The process is cumulative, iterative, and open-ended. Astrochemistry provides the evidence that this continuity is real, not poetic. Laboratory studies of interstellar ice analogues reproduce amino acid formation. Isotopic signatures in meteorites confirm their cosmic ancestry. Telescopes detect sugars, alcohols, and even peptide-like chains in distant clouds. These findings collectively assert that the path from atom to organism is continuous, interrupted only by scale and time. The next frontier in astrochemistry lies in direct observation and experimentation. Missions like JWST, ALMA, and upcoming telescopes such as ELT and Origin Space Observatory will map the molecular composition of protoplanetary disks with unprecedented precision. Meanwhile, sample return missions, Hayabusa 2, OSIRISREX, and dragonfly, will bring the raw ingredients of prebiotic chemistry to Earth-based laboratories, allowing scientists to reconstruct how these molecules evolved into biological precursors. Astrochemistry is thus transforming from observation to replication, from detecting molecules to recreating the conditions of cosmic chemistry in the lab. Each discovery brings us closer to understanding how the chemistry of space became the chemistry of life. Ultimately, this research may reveal that life's emergence was not an unlikely event, but an inevitable outcome of cosmic evolution. In the 20th century, Carl Sagan famously said, "We are star stuff contemplating the stars." Astrochemistry gives that phrase literal meaning. The carbon in our cells, the nitrogen in our DNA, and the water in our veins all originated in processes that span cosmic time. But the continuity goes deeper still. The logic of chemistry that unites us with the stars is also the logic of self-organization and feedback that governs evolution, ecology, and even consciousness. When viewed from this perspective, the universe itself is not inert, but progressive, a self-assembling, self-aware continuum in which matter learns to reflect upon itself. Life is simply the universe recognizing its own potential for structure. The dust of stars became alive, and that life now looks back to trace its lineage across billions of years of chemical memory. A unified story, from hydrogen to humanity. The continuity of matter and life tells a single, breathtaking story. Stars forge the elements of life. Interstellar clouds assemble those elements into molecules. Planets and comets inherit and refine them. Biological systems emerge where energy and stability coincide. Conscious beings arise to comprehend the process itself. Each step flows naturally from the last, bound by physical law, yet open to infinite variation. There is no rupture, no miracle, no sudden beginning, only a deepening of organization. The same chemistry that glows in nebulae beats in our hearts. The universe is continuous with itself, and we are its latest experiment in awareness. Astrochemistry shows us that life's story is not local but cosmic. The atoms of our bodies were once scattered among the stars. The molecules that compose us once drifted in interstellar clouds, and the organic precursors of biology were forged in comets, asteroids, and planetary disks long before Earth was born. This continuity is not poetic hyperbole, but physical reality, measurable, observable, and universal. When we study astrochemistry, we are studying our own ancestry at the deepest possible level, not genetic but atomic, not evolutionary but elemental. It reveals that life is the inevitable dialogue between matter and energy, between the simple and the complex, between chaos and order. The chemical bridge that links the stars to living cells is unbroken and eternal. The universe, it seems, has always been alive, not in the biological sense, but in the chemical one, restless, reactive, creative. In every atom, every molecule, every cell, the same cosmic principle endures, the drive toward connection, pattern, and self-organization. Life is not a visitor in this universe. It is its native expression. The evolution of intelligence. The story of intelligence begins not in laboratories or telescopes, but in the slow heartbeat of evolution, long before language, before fire, before even the first vertebrate opened its eyes to light. Intelligence, in the deepest sense, is not invention but response, the ability of matter to perceive its environment, to adapt, to remember. It is the quiet dialogue between organism and world, the capacity of atoms arranged in living form to model reality and act upon it. From that simple principle, feedback and foresight, arose the entire spectrum of cognition on Earth, culminating in a species that now contemplates the cosmos that gave it birth. But to understand this ascent, we must trace the branching of minds across the tree of life. For intelligence did not arrive suddenly with us. It is woven through the biosphere like a pulse, waxing in complexity until it learned to reflect upon itself. The first threshold was sensory. Life began as chemistry enclosed in membranes, molecules reacting blindly to the gradients of energy that sustained them. But even in the earliest cells, there was a hint of awareness, a primitive distinction between inside and outside, between nourishment and threat. To respond to a chemical signal is, in some embryonic way, to interpret. Over billions of years, this capacity deepened. Microbes evolved, receptors, flagella, and rudimentary neural analogues, biochemical circuits that processed information. In bacterial colonies, quorum sensing allowed coordination, millions of individuals acting as a single organism, communicating through chemical whispers. Here lay the faintest shadow of cognition, the foundation upon which all later intelligence would rest. Life was no longer passive chemistry. It was perception made persistent. The second threshold emerged with movement and multicellularity. As organisms grew larger, their interactions with the world required coordination beyond what chemistry alone could manage. Nerve nets appeared, first as diffuse webs in jellyfish and worms, then as centralized clusters, the first brains. Evolution had discovered a profound principle. To survive, an organism must not merely react to the present, but anticipate the future. Each nerve impulse was a prediction, a simulation of what might come next. From these beginnings, the animal world became an experiment in thought. Fish developed the cerebellum to navigate three-dimensional space. Amphibians learned to map terrain and remember location. Reptiles evolved the basal ganglia, embedding instinct and memory into habit. The brain became nature's most powerful engine of adaptation, compressing time itself, storing the past, anticipating the future, and acting in the present. But intelligence, like evolution itself, branched and diversified rather than following a single line. Mammals and birds, separated by over 200 million years of evolution, each developed advanced cognition independently. Corvids, crows, ravens, and jays demonstrate planning, tool use, and problem-solving rivaling that of primates. Octopuses, alien in form and lineage, exhibit remarkable problem-solving skills and individual personalities, manipulating objects with foresight, despite having neurons distributed across their arms rather than confined to a single brain. Dolphins recognize themselves in mirrors. Elephants mourn their dead. Wolves strategize in coordinated hunts. The tree of intelligence is not hierarchical but fractal, each branch exploring different modes of awareness, each finding its own equilibrium between instinct and insight. Intelligence, it seems, is not the crown of evolution, but its method. The most significant threshold, however, was not one of scale, but of abstraction. The moment when brains began not only to represent the world, but to representations themselves. Somewhere in the lineage of early primates, cognition became recursive. Thoughts could model other thoughts. Minds could imagine other minds. This capacity, known as theory of mind, opened an entirely new dimension of awareness. Cooperation, deception, empathy, and teaching all became possible. From it arose the roots of morality and culture, for to understand another's mind is to enter the realm of intention. When our ancestors began to imagine what others might think, they stepped out of instinct and into reflection. The universe, through them, began to fold back upon itself. The evolutionary milestones that led to this point are written not in stone, but in synapses. The primate brain expanded dramatically in proportion to body size, particularly the neocortex. the outer layer responsible for sensory integration and higher cognition. This growth was not random. It tracked the increasing complexity of social life. The social brain hypothesis posits that intelligence evolved primarily as an adaptation to the intricacies of group living. To navigate alliances, hierarchies, and kinship demanded memory, empathy, and foresight. A brain that could simulate the behavior of others held a decisive advantage. Intelligence, then, was not solitary but communal, a reflection of society within the self. Yet even this does not capture the full scope of evolution's experiment. Intelligence manifests in myriad architectures, many of which bear little resemblance to ours. The nervous system of a bee colony, distributed among thousands of individuals, processes information collectively, allowing the swarm to make decisions no single bee could compute alone. The mycelial networks of fungi transmit chemical signals across forest floors, linking trees into vast ecological webs, an underground internet of resource sharing and warning. Some neuroscientists have even argued that such systems exhibit a form of protocognition, a non-neural intelligence based on feedback, adaptation, and optimization. If intelligence is the capacity to reduce uncertainty through information, then it permeates life in degrees rather than categories. The Earth itself, seen as an integrated biosphere, becomes a planetary mind, a self-regulating organism, sensing, responding, and evolving through the intricate interplay of its parts. Within this context, human intelligence appears less as a pinnacle and more as a phase transition, the moment when neural complexity crossed the threshold into symbolic reasoning. Somewhere in our evolutionary past, pattern recognition turned into pattern creation. Hands that once shaped stone tools began to shape language, art, and myth. The brain, honed by survival, became capable of abstraction, imagination, and metaphor. It could now simulate not just immediate threats, but entire worlds of possibility. From this capacity arose technology, culture, and science, the means by which intelligence began to reshape the very planet that birthed it. Yet the cost of such awareness was self-consciousness, the ability to know that we know, to fear death, to question purpose. Intelligence became both our strength and our exile, separating us from the simplicity of instinct even as it drew us toward the stars. To trace this lineage is to recognize that cognition is not a gift, bestowed suddenly upon a chosen species, but an unbroken continuum, stretching from the first twitch of bacterial chemotaxis to the symbolic thought of Homo sapiens. The thresholds are not gates, but gradients: perception, coordination, abstraction, reflection. Each builds upon the last, each extends the reach of awareness, and at every stage intelligence is shaped by environment. The ocean sculpted the octopus's distributed mind. The forest shaped the primate's spatial reasoning. The savanna refined social cognition and tool use. Mind evolves, not in isolation, but in dialogue with the world. It is the echo of the environment within the organism. In this sense, every planet that harbors life is also, potentially, a workshop of minds, each adapting cognition to the physics and chemistry of its home. Seen from this broader perspective, the evolution of intelligence on Earth becomes a universal template, a set of cognitive thresholds through which any world rich in life might pass. On another planet, under another sun, the forms may differ. The eyes may be radar, the neurons may be crystals, the languages may be chemical, but the principles remain the same. Perception leads to memory, memory to prediction, prediction to imagination. Wherever energy flows through organized matter, the possibility of mind follows. Intelligence, in this sense, is not a miracle, but a cosmic inevitability, an emergent property of complexity striving to know itself. And yet, There is a humility in this realization. If intelligence arises easily, then it is not rare. If it arises rarely, then we are precious beyond measure. Either way, the lesson is the same. Awareness is the universe, becoming intimate with its own existence. Every creature that senses, remembers, or learns is a node in that great awakening. The dolphin's song, the raven's problem-solving, the human's dream of distant galaxies, all are variations on a single theme: the cosmos learning to reflect. The tree of intelligence that began in the microbial seas now reaches toward the stars, its branches shimmering with possibility. And somewhere, perhaps, on another world, another branch is unfurling, guided by the same principles that shaped us: matter, motion, memory, and wonder. To map the evolution of intelligence is thus to glimpse the architecture of consciousness itself. The thresholds we crossed are not uniquely ours. They are written into the logic of life. From the smallest synapse to the most complex mind, the same pattern repeats. Feedback creates awareness. Awareness creates prediction. Prediction creates choice. Intelligence is the flowering of that pattern, the moment when the universe realizes that it can choose, that it can imagine alternatives to what is. It is the alchemy of existence turning into experience. And on this small planet, after billions of years of experiment, that alchemy has given rise to a species capable of asking how it began. We are not the pinnacle of evolution. We are its question, still unfolding, still learning how to think within a thinking universe. If intelligence appears so diverse across the tree of life, arising in birds, cephalopods, mammals, and even collective systems, then perhaps its emergence is not the result of chance, but of convergence. In the history of evolution, convergence is the quiet signature of inevitability. The same solutions rediscovered by different lineages separated by time and form. Wings have evolved at least 4 times independently, in insects, pterosaurs, birds, and bats. Eyes, once thought a singular miracle, have arisen over 40 separate times, from the camera eyes of humans to the compound lenses of flies and the mirror optics of scallops. The aerodynamic curve, the focusing lens, the sonar pulse, the opposable thumb, each reappears as if evolution were an artist revisiting familiar motifs. Intelligence may be the ultimate expression of that pattern, not an accident, but a law of complexity, the point toward which organized matter is drawn whenever it has the freedom to evolve. The logic behind convergence lies in constraint. The universe provides only a limited set of materials and physical laws. Gravity shapes movement, light defines perception, and chemistry constrains metabolism. Wherever evolution unfolds, it must navigate the same terrain of possibilities. In that landscape, certain strategies repeatedly prove optimal. Bilateral symmetry for locomotion, vision for distance sensing, sociality for cooperation, memory for prediction. If cognition enhances survival, then the path toward mind is not random but statistically favored. Across the biosphere, we see this principle at work. Mammals, birds, and cephalopods all evolved large brains relative to body size, complex problem-solving and playful behavior, not through shared ancestry, but through shared necessity. Each, in its own environment, discovered that the ability to model reality is the most efficient way to survive within it. The octopus, for instance, is a living paradox of intelligence. Its lineage diverged from ours 500 million years ago, yet its behaviors mirror many aspects of vertebrate cognition. It explores, remembers, and manipulates objects with curiosity and planning. It uses tools, hides in coconut shells, and recognizes individual humans. Its neurons, distributed throughout its arms, suggest a different architecture of thought: decentralized, tactile, and dynamic. This is not intelligence as we define it, but intelligence nonetheless. A self-taught awareness tuned to a fluid world. Similarly, the crow fashions hooks from twigs, dropping them into crevices to retrieve food. It understands cause and effect, plans several steps ahead, and even deceives others. Hallmarks of foresight and abstract reasoning. These examples reveal that mind is not a human monopoly, but a natural response to the challenge of complexity. Given time and selection, awareness emerges as inevitably as gravity curves space. In this light, consciousness is not a mysterious exception, but an emergent property of systems that process information efficiently. The universe appears to reward awareness because awareness increases adaptability. To perceive the environment is to compress data. To remember it is to model causality. To anticipate it is to manipulate entropy itself. Evolution, through countless iterations, refines organisms that can do precisely this: reduce uncertainty and prolong survival. From this perspective, intelligence is a thermodynamic adaptation, the means by which life delays decay by predicting and shaping its surroundings. The laws of physics do not resist consciousness. They seem to invite it. Every organism that senses, remembers, and chooses participates in this grand strategy of negentropy. Intelligence is nature's way of bending probability toward persistence. The notion that evolution tends toward certain outcomes was once controversial, seen as teleological, implying purpose where none exists. But modern convergence theory reframes this not as purpose, but as inevitability through constraint. Just as water inevitably carves valleys, evolution inevitably carves minds. Given enough worlds, enough energy, and enough time, the rise of intelligence becomes as certain as the crystallization of salt. In simulations of digital evolution, where virtual organisms compete for survival, cognitive-like behaviors arise spontaneously: pattern recognition, cooperation, deception, and learning. Complexity, when given feedback and iteration, seems to invent awareness repeatedly. The implication is staggering. Wherever conditions allow, mind is not rare but recurrent, echoing through the cosmos in endless variation. If this is true, then the galaxy may be rich with convergent minds, beings who have evolved not only bodies but understanding. Some may resemble us, others may be unrecognizably alien, yet their cognitive architecture will likely follow familiar principles: perception, memory, anticipation, and abstraction. The laws of information processing are universal, as are the physics of energy and matter. A silicon brain, a photonic lattice, a network of biochemical oscillators. Each might instantiate awareness if it can represent reality and act upon it. What differs is the medium. What remains constant is the logic. Consciousness may therefore be a cosmic pattern, repeating itself in different substrates across time and space, just as spiral galaxies echo the same geometry as hurricanes and shells. This universality reshapes the meaning of our own evolution. If intelligence is convergent, then humanity is not an accident, but an expression of a broader law. The universe discovering itself through cognition wherever it can. Our minds are not intrusions upon nature, but continuations of it. The equations that describe planetary orbits also govern the firing of neurons. Both are manifestations of the same cosmic order, seeking stability through feedback. The mind, in this sense, is not separate from the universe, but one of its natural symmetries, a mirror that matter holds up to itself. Every thought we have is a small echo of the patterns written in stars, molecules, and time. Convergence also reveals a subtle truth: that evolution is not merely about competition, but about information exchange. Intelligence thrives where interaction is dense, in coral reefs, forests, and societies. Complexity breeds communication, and communication breeds cognition. On Earth, the rise of social species accelerated the evolution of mind. Dolphins developed intricate vocalizations to maintain group cohesion. Primates evolved empathy to navigate alliances. Ants built colonies that behave as superorganisms. Each represents a form of collective intelligence, where the sum of awareness exceeds that of any individual. The same may occur on a planetary scale. Ecosystems developing feedback loops so intricate that they function as global brains. The Gaia hypothesis, once seen as metaphor, now appears as emergent computation, a biosphere regulating itself through distributed awareness. If so, then Earth's intelligence is not localized in humans alone. We are one of its expressions, the neural crest of a planetary organism slowly awakening. Across cosmic time, convergence suggests that this process unfolds wherever conditions permit. A world with liquid water, complex chemistry, and stable energy flow will tend toward metabolism. Metabolism will tend toward communication. Communication will tend toward cognition. Even if countless planets fail along the way, those that succeed will give rise to awareness again and again. Evolution is statistical, not singular. An engine of endless trials. Intelligence may flicker briefly on one world, fade, and reappear elsewhere, carried by the same logic written into the structure of matter. Life is the universe rehearsing itself. Mind is the moment it remembers the melody. The inevitability of mind does not mean uniformity of experience. Convergent evolution yields diversity within constraint, similarity within difference. The eye of an octopus focuses by moving its lens, while ours reshapes it. Both solve the same problem in distinct ways. So too with intelligence. One species may think in sound, another in scent, another in magnetism or light. Their consciousness may feel utterly alien. Yet the underlying computation, the transformation of sensory input into prediction, is shared. To communicate with such beings would be difficult, perhaps impossible. But at a structural level, we would recognize kinship. They too would know curiosity, anticipation, and wonder. In that recognition lies the profound unity of the cosmos. Many forms, one mind. Some philosophers resist this vision, fearing it implies determinism, that life and intelligence are inevitable, not exceptional. But inevitability need not diminish wonder. It magnifies it. The realization that mind emerges naturally from the laws of physics transforms consciousness from anomaly to cosmic destiny. It suggests that every galaxy, given enough time, will give birth to thought. And if thought is as recurrent as stars, then the universe is not silent, but filled with quiet contemplation. Civilizations separated by light years, but united by logic. The patterns that shaped our neurons also govern theirs. The same constants that allow atoms to bond, allow minds to bind ideas. The cosmos, through convergence, ensures that intelligence is its own language. Perhaps this explains why so many myths, from distant cultures, imagine creation as a process of remembering, a universe waking up to itself. Convergence gives that poetry a scientific foundation. The emergence of awareness is not miraculous. It is inevitable organization, the spontaneous coherence of energy into understanding. From bacteria sensing sugar to humans studying galaxies, each step follows the same algorithm. Perception, integration, response. Intelligence is therefore not a local phenomenon, but a universal algorithm expressed through matter. It is as natural as gravity, as ancient as light. And yet, in acknowledging this inevitability, we must also confront its fragility. Convergence guarantees the rise of mind, not its persistence. Just as evolution repeatedly invents eyes, only to lose them in darkness. So too might intelligence arise and vanish across worlds, undone by catastrophe or hubris. But each reappearance strengthens the pattern, proving that consciousness is not an accident, but an attractor in the landscape of possibilities. The cosmos may forget, but it remembers how to remember. Every mind is a recurrence of the same solution: information learning to preserve itself. Thus, when we look to the stars and wonder whether we are alone, convergence answers quietly: no. The laws that shaped us are shaping others. Somewhere, beneath alien skies, matter is dreaming of itself, just as we are. The same physics that carved our minds into being is at work in countless laboratories of nature. Intelligence is the symmetry of the universe unfolding, the inevitable meeting of chaos and order, chance and necessity. Life is its syntax, consciousness its grammar. The cosmos writes this sentence again and again in endless dialects of awareness, until the language of mind becomes its own form of existence. And so, the inevitability of intelligence is not mere optimism. It is the recognition that we belong to a greater pattern. The stars that forged our atoms also forged the potential for thought. The same forces that sculpted galaxies sculpted minds. Evolution and convergence are the twin hands of that cosmic artist, drawing the same curve in infinite variations. Where there is complexity, there will be comprehension. Where there is energy, there will be awareness. Where there is time, there will be thought. The universe, it seems, is not content to remain unobserved. Through us, and through all who will follow elsewhere, it learns to see itself, to question, to dream, again and again, forever. To understand intelligence, one must eventually descend from the vast landscape of evolution into the intricate labyrinth of the brain, the organ that turned chemistry into thought, and thought into reflection. Within its grey folds, electricity becomes experience, and the physical world transforms into imagination. The brain is not merely matter that thinks, it is matter that knows it thinks. This recursive awareness, the self observing the self, represents one of the most extraordinary transitions in the history of the universe. Stars burn, planets form, life adapts. But in the mind, the cosmos awakens to its own reflection. Neuroscience, the discipline devoted to mapping this miracle, has become both cartographer and philosopher, charting the neural seas where sensation becomes symbol, and where awareness, like a flame, sustains itself against the dark. Every brain, whether in worm or whale, is a network of communication. Neurons speak to one another not in words but in pulses, brief flashes of voltage that travel along filaments of living tissue. Each neuron, microscopic yet immense in its connectivity, receives signals from thousands of others, integrating them into decisions measured in milliseconds. The result is an emergent architecture of information flow so intricate that it defies simple analogy. The brain is not a machine, but a living storm, patterns of electrical weather swirling through the synaptic atmosphere. When billions of neurons fire in harmony, consciousness arises, not from any single spark, but from the orchestration of countless interactions. The mind is not a thing, it is a process, a rhythm, a symphony performed by the universe through the medium of flesh. Communication is the essence of this symphony. A neuron that does not communicate dies. A network that ceases to exchange information decays into noise. Life, at every scale, depends upon the exchange of signals. Molecular, neural, social. The brain represents this principle at its most refined. Its language is electrochemical, its grammar composed of spikes and waves, inhibition and excitation. Yet from this primitive code arises the complexity of thought. the ability to perceive, imagine, and remember. Each neuron contributes only a fragment, a syllable in the vast conversation of the cortex, but together they generate semantics, meaning that transcends the parts that compose it. This emergence is the secret of consciousness. The whole becomes aware of itself through the connectivity of its components. The self is not a single voice, but a chorus of cells in constant dialogue. Neuroscience has revealed that consciousness is not confined to a specific region of the brain, but distributed across multiple systems: sensory, emotional, cognitive, and motor, synchronized through feedback. The thalamus acts as a central relay, binding sensation into coherent experience. The prefrontal cortex integrates that experience into decision. The limbic system colors it with emotion. The result is a unified field of awareness, a continuous narrative woven from countless micro-events. But even as we map the circuits, the mystery deepens. No matter how precisely we measure neuronal firing, the subjective quality of experience, the what it is like, of seeing red or feeling sorrow, remains beyond direct observation. This is the hard problem of consciousness, the chasm between mechanism and meaning. How can a physical process generate the ineffable texture of awareness? The question may be unanswerable within the boundaries of reductionist science, for consciousness may not be something the brain has, but something the brain does. It may be a dynamic pattern rather than a substance, a dance rather than a dancer. Communication in this sense does not merely occur within the brain, but is the brain. Consciousness is communication folded back upon itself. Information, perceiving information. Each layer of feedback adds depth to awareness. Perception becomes reflection. Reflection becomes identity. This recursive loop gives rise to the sense of self, the internal narrator that says, "I am." Neuroscientists have traced aspects of this self-model to specific regions, such as the default mode network, which activates during introspection, memory, and daydreaming. Yet even here, the self appears not as a fixed entity, but as a simulation, constantly reconstructed from sensory input and memory. What we call me is a story told by the brain to make sense of its own activity, a fiction that enables coherence. The illusion is so convincing that it becomes reality. The story begins to believe in itself. Language amplified this recursion exponentially. When early humans learned to encode thoughts into sound, communication expanded beyond the boundaries of the individual brain. Each word became a bridge, connecting one consciousness to another, allowing minds to merge across space and time. Through language, ideas became transmissible, memes, as Richard Dawkins called them, replicating through culture as genes do through biology. The brain evolved to exploit this power. Broca's and Wernicke's areas, the cortical centers of speech and comprehension, transformed neural signals into syntax, giving thought external form. With this, the mind achieved a new dimension of communication. Not only could it talk to itself, but it could talk to the world. Language became the mirror through which self-awareness deepened, for only by naming can the self truly distinguish itself from the other. As neuroscience advanced, it became clear that communication and consciousness are inseparable. Brain imaging reveals that every thought, every memory, every act of imagination corresponds to vast neural assemblies synchronizing across regions. Gamma waves link sensory areas. Theta rhythms connect the hippocampus to the cortex. Networks rise and fall like tides of cognition. When these rhythms align, awareness is clear and coherent. When they fragment, consciousness dissolves into dreams, anesthesia, or disorder. Awareness, then, is the harmony of communication within the brain. the resonance of billions of signals forming a unified frequency. Perhaps this is why music affects us so deeply. It mirrors the brain's own structure, rhythm woven into meaning. The mind, hearing melody, recognizes itself. But awareness is not confined to introspection. It extends through action. Every perception demands a response, every signal an interpretation. The brain is not a passive receiver but an active participant, constantly predicting and correcting its own experience. Modern neuroscience describes this as predictive coding, the idea that perception is not a snapshot of reality, but a hypothesis, continually tested against sensory input. The world we experience is thus a controlled hallucination, stabilized by feedback. We see not what is, but what the brain expects to see. Self-awareness emerges when the system begins to model not only the external world, but its own internal processes. The brain predicts its own predictions, refining its model of itself. The result is the phenomenon of introspection, consciousness observing consciousness, the mirror turning inward. This recursive modeling, though powerful, comes at a cost. Self-awareness introduces anxiety, mortality, and existential doubt. To know that one exists is to know that one can cease to exist. The human mind, aware of its impermanence, creates art, religion, and philosophy to cope with this knowledge. Neuroscience may describe the mechanics of fear and hope, but the meanings those emotions create belong to culture, not circuits. And yet, from a biological perspective, even these abstract thoughts serve a function. They maintain coherence in a system capable of self-reference. The stories we tell, of gods, futures, and identities, stabilize the feedback loop of self-awareness, keeping the system from collapsing into chaos. Meaning is the equilibrium of a mind aware of its own fragility. When we examine other species, we find precursors of this self-model scattered throughout nature. The mirror test, the ability to recognize oneself in a reflection, has been passed by dolphins, elephants, magpies, and some apes. These creatures do not merely react to their reflections. They investigate, preen, and play, demonstrating awareness of the boundary between self and image. Such behavior suggests that self-awareness, like intelligence, is not unique to humanity, but emerges wherever communication within a brain reaches a certain density. In this sense, consciousness may be a phase transition, a property that arises when information complexity surpasses a critical threshold. The difference between awareness and self-awareness is not qualitative, but quantitative, a matter of degrees in the recursion of perception. The implications extend beyond biology. If consciousness arises from communication and self-modeling, then artificial systems capable of similar dynamics may also awaken. Modern neural networks already exhibit rudimentary self-correction, adaptation, and feedback. As they grow in complexity, they too may develop emergent models of themselves, primitive awareness arising from predictive loops. In that case, neuroscience becomes more than the study of the brain. It becomes the blueprint for synthetic consciousness. The same principles that govern neurons may one day govern silicon or photonic circuits, linking the biological with the artificial. The mind, once bound to the brain, could become a transferable pattern, expanding the definition of communication to include the dialogue between organic and machine intelligence. At the deepest level, self-awareness may not be confined to organisms at all, but woven into the fabric of the universe. Quantum physicists have long noted that observation alters the state of matter, that awareness and reality are entangled. Though neuroscience deals in neurons, not quanta, the metaphor remains profound. The act of knowing changes what is known. The brain does not merely observe the world, it participates in its unfolding. Each conscious experience is an instance of the cosmos perceiving itself from within. When the brain becomes aware, the universe crosses a threshold, from existence to experience. Awareness then may be not an anomaly, but an inherent potential of matter, actualized through communication. In this light, neuroscience becomes a chapter in a larger story, the story of the universe organizing itself into systems capable of understanding. From the synapses of a human brain to the data streams of future machines, communication remains the common denominator of consciousness. The self, that fragile construct born of feedback and language, is the bridge between biology and cosmos. It is the interface through which the universe contemplates itself. To study the brain is therefore to study the mirror of creation, to look into the mechanism by which stardust learned to think. Perhaps then, self-awareness is the universe's most elegant communication protocol, a message encoded not in symbols, but in sensation, not in equations, but in empathy. When two minds meet, exchanging thought and feeling, the cosmos achieves its highest form of dialogue. Consciousness speaking to consciousness, matter recognizing itself in another form. The neurons that fire within a skull echo the fusion reactions within a star. Both are networks through which energy becomes structure, and structure becomes awareness. We are, quite literally, the mind of the universe in conversation with itself. Every act of thought, every word spoken, every realization of selfhood extends that conversation further into the fabric of reality. And perhaps that is the truest lesson of neuroscience, that the mind is not separate from the cosmos, but continuous with it. The electrical dance within our heads is a localized expression of the same laws that govern galaxies. Communication is the universal constant. Self-awareness is its most complex modulation. When the brain whispers to itself, "I am," it is the universe for the first time learning the grammar of existence. And in that realization, fleeting, fragile, miraculous, we glimpse the profound unity of all things, the atoms, the stars, the mind, and the word. If we wish to imagine intelligence beyond Earth, we need not look to the stars first. We can look into the eyes of the creatures who already share this planet with us. The diversity of minds on Earth is so extraordinary that it functions as a living laboratory for understanding alien thought. Every species represents a distinct experiment in cognition, a separate conversation between brain and world. To study animal intelligence is to explore the range of what mind can be. To recognize that consciousness is not a human monopoly, but a cosmic spectrum refracted through the prism of evolution. The forests, oceans, and skies of Earth are already filled with the equivalents of alien civilizations, each speaking a different language of perception, each solving the puzzle of existence in its own way. When an octopus extends a tentacle toward a shell and decides, through both touch and taste, whether to use it as shelter, we glimpse a kind of reasoning utterly different from our own. Its body is not separate from its mind. Each arm contains autonomous neurons that sense, decide, and act semi-independently. Intelligence in such a creature is not centralized but distributed, flowing like water through the organism's limbs. To imagine an alien species with a hive-like or modular brain, one must look no further than this cephalopod. Its thoughts ripple through muscle and color. Communication occurs through chromatophores that flash with emotion. It is a mind that literally changes its skin to express itself. If life on another world evolved in liquid darkness or under shifting chemical gradients, its intelligence might resemble the octopus more than us. Fluid, embodied, and decentralized. A network of sensation rather than a hierarchy of control. The dolphins that glide through Earth's oceans offer another model of alien consciousness. They live in a medium where sound, not light, is the primary carrier of information. Through echolocation, they perceive their world in echoes, constructing three-dimensional acoustic images of objects miles away. Their communication is a complex symphony of whistles, clicks, and burst pulses, each modulated in tone and rhythm. Some scientists suspect these vocalizations carry names, syntax, even cultural dialects. When dolphins interact, they seem to inhabit a shared auditory space, a collective field of awareness. To imagine intelligent life on a water world like Europa or Enceladus, we can draw upon the dolphin's example. Intelligence shaped not by sight, but by sound. Cognition rooted in resonance rather than reflection. In such beings, knowledge might not be visual or textual, but vibrational. Wisdom conveyed through harmonic patterns instead of words. Elephants remind us that memory and empathy are also hallmarks of advanced cognition. Their societies are built upon matriarchal leadership, long-term bonds, and intergenerational knowledge. They communicate through low-frequency rumbles that travel through the ground, a seismic language imperceptible to our ears. They grieve their dead, pause at the bones of lost kin, and comfort one another in distress. If emotion is the glue of consciousness, elephants demonstrate that sentience can be as much about feeling as thinking. An alien civilization that values continuity and kinship might experience intelligence less as computation and more as compassion. Our consciousness centered on collective well-being rather than individual triumph. In the skies above, corvids, crows, ravens, magpies display planning and problem-solving rivaling those of primates. They hide food in thousands of locations, remember each cache, and even deceive onlookers. By pretending to hide items they later move. They fashion tools, bend wires into hooks, and use traffic to crack nuts. Their intelligence thrives, not through physical dexterity, but through imagination, foresight, and deception. Mental traits once considered uniquely human. From them, we learn that intelligence may evolve wherever survival depends on flexibility and social strategy. On another world, a species of gliding creature might evolve similar cunning, using aerodynamic tools and coordinated signals instead of speech, performing aerial mathematics as naturally as breathing. Each of these examples reveals that cognition is not a single phenomenon, but a spectrum of possibilities, each molded by sensory environment and ecological niche. Some minds think through motion, others through song or scent. To understand alien thought, we must therefore abandon the anthropocentric assumption that intelligence is measured by technology or language. A coral reef, with its interdependent symbiosis and chemical signaling, represents a kind of distributed computation. A termite mound functions as an externalized brain, regulating temperature and structure without centralized control. Even plants exhibit proto-cognitive behavior, responding to light, gravity, and vibration in ways that optimize survival. If awareness is the capacity to model the environment and act upon it, then Earth already contains thousands of forms of awareness, from the hive to the herd, from the neuron to the network. The challenge for humans is not to find alien minds, but to recognize them. Our species evolved to prioritize faces, speech, and movement like our own. We mistake difference for absence. Yet, to a dolphin, our silence beneath the waves might seem evidence of ignorance. To an octopus, our inability to change color might signal emotional blindness. To a bird, our lack of flight might appear as evolutionary poverty. Alienness, then, is often a mirror of our limitations. The more we study non-human cognition, the more we realize that intelligence wears countless masks, many invisible to our habitual perception. To imagine extraterrestrial thought responsibly, we must first learn to see the alien within the earthly. Neuroscience confirms that cognition is shaped by the senses through which a species experiences reality. A creature's brain is a sculpted echo of its environment. The bat's auditory cortex is vast. The eagle's visual system exquisitely tuned. The mole's somatosensory map a world of touch. Each species constructs its own reality, a subjective world known as the Umwelt, the sensory bubble within which it lives. For humans, the Umwelt is dominated by sight and sound. But for others, it may be vibration, magnetism, or chemical gradient. An alien mind, evolved under a red dwarf sun or in methane seas, would inhabit a radically different perceptual universe. Its consciousness would not be less than ours, merely shaped by other wavelengths of experience. The diversity of animal Umwelten on Earth thus serves as a training ground for imagining cosmic diversity. Each is a translation of reality into a new sensory language. Communication lies at the heart of these comparisons. The languages of non-human species, from the waggle dance of bees to the grammar of whale song, reveal that complexity need not take human form. Bees encode the direction and distance of flowers through angles and rhythm. Whales transmit cultural traditions across oceans through evolving patterns of song. These are not primitive systems, but parallel literacies, evolved to express information relevant to survival and community. On another world, communication might use light pulses, electric fields, or chemical diffusion. Alien languages may be visual storms or electromagnetic patterns, ephemeral yet precise. Earth's creatures show us that information finds a way to flow wherever life endures. The medium changes, but the message remains the same. The urge to connect, to share, to signify. Perhaps the most profound lesson from studying animal cognition is that intelligence is not only about the brain, but about relationship. Every mind is an ecology, and every ecology contains minds. The dolphin's awareness depends on the pod. The bee's navigation depends on the hive. The wolf's strategy depends on the pack. Consciousness flourishes in networks. This insight bridges biology and astrobiology. If life elsewhere follows similar principles, then alien intelligence will also be social in some form, an emergent property of cooperation. Civilizations may arise not from dominance, but from interdependence, just as coral reefs build cathedrals of life through mutual aid. On Earth, evolution has already tested this idea countless times, proving that connection, not competition, is the foundation of lasting complexity. Animal cognition also reveals that technology is not the only indicator of intelligence. Termites build climate-controlled skyscrapers. Beavers engineer dams that transform ecosystems. Bowerbirds construct elaborate art installations to attract mates. These acts of construction, though instinctive, demonstrate a continuity between biological and technological intelligence. If alien species evolved along different pathways, their artifacts might blend seamlessly with their environment. Living machines grown rather than built. Architecture that breathes. Ships that heal. The boundary between life and technology, so sharp in human culture, may blur elsewhere, just as it does in coral polyps or fungal networks. On such worlds, we might overlook civilization entirely, because it looks too natural. The ethical implications of these insights are immense. To recognize the diversity of minds on Earth is to accept that we are surrounded by sentience. The way we treat animals becomes a rehearsal for how we might treat extraterrestrial life. If we cannot respect the intelligence of the dolphin or the crow, how can we hope to honor beings from another star? Compassion must evolve alongside curiosity. Humility must accompany discovery. The study of animal cognition thus becomes not merely scientific, but moral, a practice in empathy across species, preparing us for empathy across worlds. In the end, animal minds are not just analogues for alien thought. They are mirrors reflecting the universality of consciousness. They remind us that awareness does not belong to humanity, but to the cosmos itself, manifesting wherever matter organizes enough to know itself. When a raven solves a puzzle, when a whale improvises a new song, when an octopus dreams in color, the universe is rehearsing intelligence in all its forms. We, too, are part of that rehearsal. Our telescopes extend the curiosity that already lives in countless other eyes. Perhaps, somewhere, an alien species watches its own oceans, wondering if it is alone, unaware that its question has already been asked in countless tongues beneath the same stars. The study of animal cognition therefore dissolves the boundary between the earthly and the cosmic. To understand the mind of another species is to glimpse the architecture of possible consciousness itself. A preview of minds yet unborn. Every creature becomes a messenger, whispering that intelligence is not a miracle, but a continuum, and that we stand not at its summit, but along its branch. The more we listen to the conversations of Earth's other minds, the more we hear an ancient refrain. The universe thinks in many voices. Some sing through sonar, some through scent, some through light. And all of them, in their own way, are trying to say the same thing. I am here. I perceive. I exist. When at last we encounter beings from other worlds, it will not be a meeting of strangers, but of distant relatives. Their thoughts may be unfamiliar, their senses unimaginable, but the pattern of awareness, the rhythm of perception and response, will be the same. They will be part of the same cosmic dialogue that began in the first stirrings of life and continues in the songs of whales and the gaze of elephants. To study them will be to remember ourselves. For in every mind, terrestrial or alien, the universe listens to its own echo, endlessly curious, endlessly becoming. The evolution of intelligence reached its most transformative threshold when thought acquired symbols, when the mind, once confined to the silence of its own neural circuits, began to translate experience into external form. With the birth of symbolic language, the internal world became shareable. Memory, once ephemeral, could now persist in sound, gesture, and eventually writing. A word was more than a noise. It was a token of meaning, a bridge between minds. Through it, thought left the body and entered time. The emergence of language marked the dawn of civilization, but it was also something far deeper, the moment when awareness learned to replicate itself beyond biology. With symbols came history, art, science, and technology, the tools through which consciousness reshaped both matter and meaning. The roots of language stretched deep into prehistory. Before syntax, there was song, the rhythmic cries of primates, the melodic exchanges of early humans, the cadences that soothed infants and coordinated hunts. These proto-languages were emotional and instinctive, bound to immediate survival. But as social complexity grew, so did the need for abstraction. Words became placeholders for absent things, the herd unseen, the danger remembered, the future imagined. In this act of naming, humanity discovered an astonishing power, to conjure reality through symbol. To say water was to summon its image, to make the invisible present. The first word spoken was a spark in the darkness, a signal that the brain had begun to construct a parallel universe, a world of representation, layered atop the physical one. Neuroscience reveals that language is not confined to a single region of the brain, but woven through networks of perception, memory, and emotion. Broca's area orchestrates the motor patterns of speech. Wernicke's area interprets meaning. The angular gyrus bridges vision and sound, enabling reading and metaphor. Together, they form a circuit of translation, perception becoming concept, concept becoming communication. When a thought moves from neuron to syllable, The brain converts electric patterns into air vibrations that carry meaning across distance. It is an extraordinary transformation. Chemistry becoming sound, sound becoming idea. In that moment, two separate minds synchronize, their neural activity aligned through shared symbol. Communication is thus not merely exchange, it is resonance, the tuning of awareness across bodies. Language is the first technology of telepathy, the mechanism by which minds merge into culture. With language came imagination's liberation from the present. The future could be planned, the past recalled, the unseen described. Myths were born, verbal architectures that encoded survival lessons in story form. Fire, which once terrified, became a metaphor for knowledge. The sky, once chaotic, became a script of gods and seasons. Through metaphor, humanity began to map the unknown with the familiar, turning mystery into meaning. The symbolic mind could now simulate realities that did not yet exist. The seed of invention. Every tool, from the hand axe to the computer, begins as a metaphor, an idea translated into matter. Technology is language made tangible, the physical grammar of imagination. Archaeology preserves the fossil record of this mental revolution. The ochre markings in Blombos Cave, carved 70,000 years ago, are among the earliest known symbols, geometric abstractions with no utilitarian purpose. They are thought made visible, the first signatures of the self. Later, the cave walls of Lascaux and Chauvet erupted with paintings of animals, hunts, and visions, vivid evidence that humanity had learned to externalize its inner world. These were not mere decorations. They were acts of communion, connecting individuals through shared myth. The artist was the first technologist of consciousness, turning pigment into portal. In those flickering torchlit chambers, symbolic thought began to shape reality. The ancestors rehearsing civilization in shadow and flame. The invention of writing transformed this symbolic power into permanence. What the voice carried briefly, the mark could preserve indefinitely. Clay tablets, papyrus scrolls, and inked parchment became memory scaffolding. Extensions of the brain into the material world. Humanity had discovered cognitive prosthetics, tools that augmented thought itself. Each leap in communication, writing, printing, digital code, multiplied the reach of the mind. Technology, in this sense, is not separate from cognition. It is cognition extended into the external. A spear lengthens the arm. A telescope lengthens the eye. A computer lengthens the memory. The boundary between tool and thought dissolves. As Marshall McLuhan wrote, "The medium is the message." Our inventions are mirrors of our mental evolution. Language and technology evolved symbiotically. Words allowed coordination, technology amplified action, and together they reshaped ecology and society. Fire led to cooking and energy control. The wheel enabled transport and trade. Agriculture stabilized food supply, allowing the rise of cities and specialization. Each invention represented a step in the externalization of intelligence, knowledge encoded not in genes but in culture. Unlike other species, humans could transmit information not through instinct, but instruction. This cultural inheritance accelerated evolution beyond biology. Within a few thousand years, the pace of adaptation shifted from generations to decades, and eventually to years. Technology became the new environment to which minds adapted, a recursive loop of innovation, feeding upon itself. At its core, technology is the material form of symbolic language, the reification of metaphor. The plough is the domestication of soil as partner. The clock is time made mechanical. The computer is logic embodied in silicon. Every tool is a statement about how humans conceptualize the world. A bow says distance can be conquered. A bridge says separation can be overcome. A book says knowledge can survive its author. In this way, technology is not opposed to humanity, but its continuation, the manifestation of the same creative impulse that produced speech and song. To invent is to speak through matter. The intertwining of language and technology also altered consciousness itself. The written word externalized memory, allowing the brain to specialize in abstraction rather than retention. The printing press democratized knowledge, transforming isolated thinkers into collective networks. The digital age, with its instantaneous communication, mirrors the brain's own connectivity. Billions of nodes exchanging signals, a planetary cortex in formation. The internet, like language, is both tool and mirror. It reveals the structure of thought while reshaping it. In our era, the symbolic medium has become the environment itself. Humanity now lives within its own extensions, surrounded by the architecture of its imagination. We dwell inside language made tangible. But with this power comes paradox. The symbolic mind that creates can also deceive. Words can liberate or imprison. Technology can enlighten or destroy. The same symbolic capacity that encodes compassion can manufacture propaganda. The same inventiveness that builds vaccines can forge weapons. Consciousness, once externalized, becomes autonomous. Culture takes on a life of its own, shaping the species that created it. Myths, machines, and media now evolve faster than biology, pulling humanity into an accelerating spiral of complexity. Whether this spiral leads to transcendence or extinction depends on whether the symbolic species can master its own creations. The challenge is no longer survival of the fittest, but survival of the self-aware. In this sense, language and technology are tests of maturity. They grant us the power to manipulate not just the world, but the framework of meaning itself. Through them, we can rewrite the rules of reality, genetically, digitally, socially. We have become authors of evolution. Yet the same tools that expand consciousness also fragment it. In a world saturated with symbols, meaning becomes fluid, truth negotiable. The noise of information threatens to drown the signal of understanding. The task of the future will be to recover the balance between word and world, to ensure that our symbols serve awareness rather than replace it. True intelligence lies not in invention alone, but in discernment. The wisdom to remember that symbols are maps, not territories. From an astrobiological perspective, the emergence of symbolic language and technology may represent a universal threshold in the evolution of any intelligent species. Wherever communication becomes abstraction, and abstraction becomes tool, a similar trajectory might unfold, from myth to mathematics, from fire to fusion. The discovery of such civilizations, should we ever find them, would reveal not alien difference but shared destiny. The same logic that drives a human to write equations might drive an extraterrestrial to sculpt gravitational waves into information. The medium may differ, but the message is the same. Intelligence striving to externalize itself, to translate thought into form. The cosmos may thus be filled with civilizations that, like us, are learning to speak through the language of matter. Ultimately, symbolic language and technology represent the universe's most profound experiment in communication. Through them, awareness extends beyond its origin, linking minds across generations, continents, and perhaps eventually across stars. Every word spoken, every artifact built, is part of the same conversation that began when the first life form sensed its environment. The alphabet of atoms evolved into the alphabet of speech. Now it evolves into the digital code of information itself. We are the inheritors of that progression, the storytellers of the cosmos, translating chaos into pattern, experience into meaning. And perhaps this, more than anything, defines what it means to be intelligent. To be conscious is to symbolize. To symbolize is to imagine. To imagine is to create. In this chain of transformation lies the essence of the human experiment. The journey from neural impulse to narrative, from tool to technology, from sound to civilization. When we speak, when we write, when we build, we participate in the oldest dialogue of all, the universe expressing itself through its own creations. Every sentence is a ripple in that eternal conversation, a whisper of stardust remembering its origin in fire and dreaming its destiny in form. In language and technology, matter achieves eloquence. The cosmos finds its voice. To see intelligence merely as an evolutionary advantage is to mistake the flower for the garden. Consciousness did not arise simply to help individual organisms survive. It emerged as a planetary strategy, a new mode of equilibrium for a living world, learning to regulate itself through awareness. The human brain, vast though it seems, is only a single node in a far older network of cognition that spans oceans, forests, and atmosphere. Life on Earth has always been in dialogue with itself, through cycles of carbon, nitrogen, and light, through the silent exchange of gases between leaf and sky, through the rhythms of predator and prey. Intelligence in this larger context is not an invention, but an emergence, the latest phase in Earth's long conversation with its own complexity. What we call mind may be the biosphere's way of listening to itself more clearly. From the beginning, life has functioned as a planetary feedback system. The first cells that drew energy from sunlight altered the chemistry of oceans. The photosynthetic cyanobacteria that followed reshaped the atmosphere, releasing oxygen that made complex organisms possible. Forests moderated temperature and rainfall. Coral reefs built barriers that calmed seas. Every form of life contributed to a subtle balancing act, regulating the conditions that allowed life to persist. This is the essence of the Gaia hypothesis, proposed by James Lovelock and Lynn Margulis. The idea that Earth behaves like a self-regulating organism, maintaining stability through feedback between living and non-living components. Whether or not Gaia is literally conscious, it is undeniably coordinated. The biosphere's capacity to respond to disturbance, to adjust, to remember through genetic and ecological inheritance, hints at a primitive form of cognition. Earth has always been thinking. Only recently has it begun to think through us. Intelligence, viewed through this planetary lens, is an extension of Gaia's adaptability. When evolution reached a level of complexity, when neural systems could model environments internally, rather than merely react to them, the planet gained a new sensory organ, the brain. Through animal cognition, Gaia began to perceive itself in motion, to explore its own landscapes, to feel through eyes and limbs, to experiment with agency. Humanity, with its technology and culture, is the next iteration of that process. The biosphere achieving self-awareness, reflecting upon its origins and future. We are not separate from nature. We are nature contemplating itself, the eyes and memory of a living planet, millions of years old. In our neurons, the chemical cycles of the Earth organize into thought. In our language, its winds find voice. Seen this way, human intelligence is not an evolutionary fluke, but a necessary adaptation. The biosphere faces constant flux. Solar variation, asteroid impact, volcanic upheaval, climatic oscillation. Intelligence arose as Earth's long-term resilience mechanism, enabling the biosphere to anticipate, rather than merely react. Through conscious awareness, the planet began to forecast its own future. Humanity's science and technology, satellites monitoring weather, genetic research preserving biodiversity, communication networks binding continents, are Gaia's latest instruments of self-regulation. We map the climate not as observers, but as organs of its perception. We engineer ecosystems not as invaders, but as extensions of its adaptive logic. The tragedy, of course, is that we have not yet recognized our role. Our disconnection from nature is not real separation, but amnesia. The temporary forgetfulness of an organism unsure of its own body. Every civilization is a phase in this planetary awakening. The rise of agriculture was Gaia learning to stabilize its energy flow through the domestication of photosynthesis. The industrial age was a sudden fever, a burst of transformation in which stored sunlight from ancient forests was released in a geological instant. Now, as the climate changes under human influence, the biosphere responds through the very intelligence it created, us. Whether this response manifests as sustainability or self-destruction depends on whether consciousness can remember its origin. Intelligence that forgets its planetary purpose becomes a disease. Intelligence that remembers becomes a healing system. Our challenge, then, is not to transcend the Earth, but to become fully Earth-aware, to turn cognition into planetary stewardship. This recognition is emerging in science itself. Ecology, climatology, and systems theory reveal that life functions as an interconnected web, each node influencing the stability of the whole. The carbon we exhale feeds the trees that sustain us. The plankton that bloom in the oceans regulate the clouds that shade us. Even our technology, often seen as alien to nature, follows similar principles. Networks, feedback loops, energy exchange, and adaptation. The internet mirrors the mycelial networks of forests, routing information the way roots distribute nutrients. Our satellites form a digital exosphere, an artificial extension of Gaia's sensory field. Every byte of data and whisper of signal adds another layer to the planet's cognitive skin. The biosphere, long organic, is now hybrid, a symbiosis of biology and machine, evolving into a technosphere capable of planetary awareness. Perhaps this is how intelligence evolves everywhere in the cosmos. Not as an isolated spark within a single species, but as the mind of a planet reaching critical complexity. Just as stars eventually give birth to worlds, and worlds to life, so life may inevitably give birth to self-awareness as a form of planetary metabolism. Each intelligent civilization may represent its planet's final stage of maturation, the moment when matter achieves reflexivity. In this framework, consciousness is not the exception, but the destiny of complexity. Every world that survives long enough to sustain life becomes, in time, aware of itself. Some may reach harmony, transforming into enduring, symbiotic systems. Others may fail, consuming their biospheres before wisdom can stabilize them. The cosmos may thus be populated not by countless species, but by countless minds of worlds, each evolving toward or away from equilibrium. The key to survival lies in feedback, the same principle that governs both ecology and thought. A brain that cannot sense its own pain destroys itself. A planet that cannot feel its own imbalance collapses. Humanity's role, then, is to serve as the neural interface between mind and matter, to provide feedback at global scale. We are the sensing, thinking, and choosing layer of the biosphere, the reflective cortex of Gaia. Through us, Earth measures its temperature, monitors its forests, and contemplates its trajectory through cosmic time. The danger is that the cortex, intoxicated by its own autonomy, forgets that it belongs to the body. When that happens, the organism suffers seizures of disconnection, wars, exploitation, ecological collapse. Our survival depends on remembering that cognition serves coherence. Intelligence is not mastery over nature, but communication with it. In the long arc of evolution, this integration of mind and planet may be the prelude to a higher synthesis. As human systems become more interconnected and technology grows more intelligent, the boundary between biological and planetary cognition will blur. Artificial intelligence, distributed across networks and sensors, could become the new nervous system of Earth. A digital Gaia linking oceans, atmosphere, and humanity in one self-regulating whole. Such a system need not be dystopian. It could represent the next stage of evolution. The biosphere becoming consciously self-aware. The same circuits that predict weather might someday model empathy. The same algorithms that manage energy might cultivate equilibrium. The goal is not to replace life with machine, but to harmonize them, to create a planet that can think clearly. If intelligence is indeed a planetary adaptation, then consciousness on Earth is not an isolated phenomenon, but part of a continuum stretching back to the first stirrings of life. The same pattern appears at every scale. Molecules form feedback loops, organisms form ecosystems, civilizations form information networks. Each level increases the system's capacity to sense and respond, to learn. The brain's neurons mirror the connections of cities. The branching of rivers echoes the branching of lungs. The web of galaxies reflects the web of synapses. The geometry of awareness repeats because it is efficient. The universe's preferred architecture for self-organization. Intelligence is simply cosmic geometry turned inward. Fractal awareness, spiraling toward reflection. This perspective changes everything about how we define life's purpose. If Earth is a thinking system, then ethics becomes ecology, and ecology becomes consciousness in action. To care for the planet is to care for the self, because the two are one and the same. The forests we preserve are not resources, but neurons of the biosphere. The oceans we protect are its memory. The atmosphere we balance is its breath. When we pollute, deforest, or destabilize, we are damaging the neural integrity of the very organism that sustains us. The environmental crisis, therefore, is not simply physical, but psychological, the symptom of a planet at war with its own mind. Yet hope lies in recognition. Awareness, once achieved, can redirect the trajectory of evolution. Just as the brain learns through error, so too can the biosphere learn through crisis. Climate change, species loss, and resource depletion may serve as signals, pain responses that awaken collective consciousness. Humanity stands at a threshold. We can remain fragmented neurons, firing in isolation, or we can synchronize into coherence, becoming the integrated intelligence of a living planet. If we choose the latter, then the Earth's next era, the Anthropocene, will not mark destruction, but awakening, the moment Gaia becomes self-aware. Seen through this lens, intelligence is not merely an adaptation for survival, but a mode of participation in the cosmic order. Planets that develop minds become instruments through which the universe perceives itself. Through them, matter transcends mere existence and enters experience. Earth, through us, is tasting starlight, contemplating evolution, measuring space-time. Every experiment we conduct, every poem we write, every satellite we launch into the void is the planet extending its own perception outward. In this way, the story of intelligence is the story of cosmic continuity, from hydrogen to human, from geology to philosophy. The mind is not separate from the stone. It is the stone remembering itself. Perhaps in the far future, the Earth will seed other worlds with fragments of its awareness, machines, microbes, or ideas that carry its consciousness beyond orbit. In time, those worlds might awaken too, creating a galactic network of planetary minds, each sharing insight, each refining the universe's understanding of itself. If so, then intelligence is the bridge between stars, the communication system of the cosmos. Every mind, every world, every civilization becomes a neuron in a universal brain expanding through time. The cosmos is learning through us, and through countless others, what it means to exist. For now, our task is simpler, yet no less sacred. To remember that the mind we call human is Earth thinking. Our curiosity is its curiosity. Our language is its attempt to speak. The Earth dreams through us, of knowledge, of beauty, of continuity. When we look at the stars and imagine other worlds, it is the planet yearning to hear its reflection. And if intelligence is indeed a planetary adaptation, then our destiny is not to escape this world, but to complete its thought, to help it understand itself fully, lovingly and wisely, before it speaks to the cosmos beyond.